maybe you have the vertical and invariant vector field, and this will be the infinitesimal gauge transformations. And what is nice about these things, which at least something at the structure it's really useful in my ways. By the way, this was done by Atiyah in '57. Is that if you split this sequence, the second one, so if you just lift the vector fields from the base space to the total space, this is a way to give a connection, even a gauge connection. And also, there is a natural action of this Lie algebra on these splittings. So you are realizing the splittings as connections, and then the gauge transformation as an action of this vector field on these connections. And okay, there is an abstraction. This means that not everywhere in the sense, not on all spaces there is a connection. For instance, if you are doing at a holomorphic level, it's not true that in general there is a connection. If you're working at a smooth level, actually you can show that this is zero, there is always a connection. So what is then the object that we start with, a non-commutative principal bundle? We need to dualize everything that I did before. So instead of spaces, we need to talk about algebras. Instead of action, we need to talk about coactions. And then instead of invariant, we need to talk about co-invariants. So P over M with the structure group G. P will be replaced by an algebra A. And then the structure group will be replaced by an Hopf algebra H. There is a co-action of this H on A, which I will write it like that, and is also useful Zwiedler notation. So here is even, a sum is to be understood, in the sense that there is a double sum. The first element here is in A, the second element is in H, and they have the sum of all these things. So, and what is left alone by this coaction, you call it B. This is a subalgebra. And so this will be the algebra of functions over the base space. So A is the algebra of functions on the total space. H is the structure of algebra, and this is the base space algebra. There is some conditions for which this is really a principal action. So something that says that you are really doing a non-commutative principal bundle. And the principality is just via what is called a canonical Galois map. So you have a fibered product, and you just map it to this usual product. So a pair of functions are mapped in these things here. You see, 0 means that you are in A, and 1 means that you are in H. Also, the label will tell you where you are. So if this is an isomorphism, then you say that you have a non-commutative principal bundle, or maybe an Hopf-Galois extension, or whatever. Okay, there are some technical things here I will skip. This is the way in which I'm dualizing things. So at an algebraic level, so if you have a principal bundle, a usual principal bundle, then like I was saying, A are the coordinate functions on P, B are the coordinate functions on the base, and H are the coordinate function on the group, and this is an Hopf algebra. So really, what I'm doing, I'm dualizing. So in particular, what I was writing like A tensor A over B, this is really the fibered product, like I was saying. And so the principality of these bundles is the fact that this map here is bijective, is really the dual of what I was saying before, that the canonical map, the Galois map, is really an isomorphism. So again, what I was saying, one way to think of the gauge transformation of a principal G bundle is that we are the group of G equivariant maps. So, equivariant maps from the total space into the group, or as automorphisms of your bundle, which are vertical. I mean, they do not move the base point. So there are these two versions here. This is already classic, still classically, sorry. But I can work it algebraically. So instead of talking about action, I need to take coaction. And so here is a way to do it. I mean, that now we have maps from, all the arrows need to be inverted. So we have maps now from H into A, which are equivariant. So they are compatible with the coaction. Or vertical automorphism, that again, they are compatible with the coaction. So you can work at the level of algebras already at that level. And of course, this is written in a way that you can, you don't need H or B to be commutative. There can be more general objects. Okay, in fact, that's exactly what I was writing, is that now you take unital algebra maps from A into itself, which are compatible with the coaction of your structure of algebra. And so this will be a way to implement that. And you have an inverse. This is a group. And in fact, any such map is automatically invertible. And so you have really something which is very nice. Okay, so what is then this algebroid? For the moment, I'm only writing a B algebroid because, I mean, like I said, the antipode need not exist in general. So classically, so you have your principal bundle, which I was writing before, and then you construct the gauge groupoid, so the Ehresmann groupoid, by taking the diagonal action of your group on P cross P, and then you take two quotient. And this is a groupoid, in the sense that also Beppe was talking about yesterday. And there is a source map and there is a target map, so everything is really compatible. And here I just want to do something dual. So I have then this non-commutative principal bundle, so an Hopf-Galois extension. I have this coaction, which I write it like that. I mean, what is here written as a translation map was the inverse of these Galois maps. And so I take the co-invariant elements of the diagonal coaction. So the Ehresmann one was just the diagonal action. I just take the diagonal coaction. So I just take any two functions, A tilde, I'll think of them as in A cross A, and then I will ask that they are invariant or co-invariant for this coaction. Okay, this is just this is just a way to say that this object is an algebroid over B rather than over C. So there is a coproduct, there is an there is a coproduct, there is an antipode, there is also a product. So this object is really a B algebroid. So there is a product, like there is a bialgebra, there is a product and a coproduct, and they are compatible, and there is a counit. So this is really exactly the same object. And okay, sorry, I made some mistake here. No, okay. If you just consider an Hopf-Galois extension and you construct what I was writing before, this object here, I can prove that this object, there is an antipode for these things. And the antipode is done via a universal R matrix. Here, I will tell you in a moment what does it mean R to be quasi-triangular or whatever. But this is essentially to think of it as the generalization of the flip, dualized. I mean, classically, when you just move things around, you just flip them. But so if everything is commutative, you don't mind much. But if your algebra is non-commutative, you need something more sophisticated. So you need an R matrix which will just flip things around, in a sense. And for the non-commutative principal bundle, using R matrix for the structure of algebra, you can construct an antipode. And this obeys all property for an antipode. So this is really something which you will call it an algebroid, because it's not an algebra, it's something more general. If now I have this gauge algebra, B algebroid, what is now a bisection? A bisection will be something which is mapping your algebroid into B. So in a more technical sense, these are called left characters, unital maybe, and bilinear. The collection of all these bisections is a group. It's a group, and there is a convolution product. And one is a little bit complicated from a notational point of view, because you have to write your coproduct is in 1 and 2, so there is one component and the second component in this Zwitter kind of notation. And then you have this strange product here. 1 and 2 up here was a way to keep track of what I was calling the translation map. It's a little bit sophisticated complicated from a notational point of view, but you have a coproduct here, and you use it to give the convolution product. And these are actually a way to give gauge transformation. So there is a group isomorphism. There is a group isomorphism between the bisections of the algebroid with the bundle automorphisms, and it's written here explicitly. So these bisections may be a way also to give gauge transformations. Okay. There are many examples of this construction. And so, for instance, the monopole bundle over the quantum SU2, all these SU2 bundle over these theta spheres, or maybe these orthogonal bundles over the even dimensional theta sphere. To get a better handling of this object, I will rather go to I will rather go to derivations, so vector fields, rather than automorphisms, so infinitesimal gauge transformations. And I will construct these Atiyah sequences of Lie algebra of derivation, which in addition, they are braided. At the beginning, I was writing this thing here, this thing here. So this I will call it Atiyah sequence, and I will just give an analog of this sequence for these non-commutative bundles. Okay, so an Atiyah sequence of braided Lie algebras of derivation. You tell me when 5 minutes to go, because I lost track. Okay. So here is the dual version of this triangular or quasi-triangular structure. So I will consider then a principal bundle, non-commutative principal bundle, and in addition, there will be an external Hopf algebra of symmetry, K, and so there is an action of K on this bundle, which is compatible. And I will take it to be triangular, or maybe quasi-triangular. I mean, before I was writing quasi-triangular. I did not want to just, it's already complicated from a notational point of view. I did not want to write many formulas. So I'm giving here the triangular or quasi-triangular version. So there is an element here in K cross tensor K, so a universal R matrix, which will satisfy also the Yang-Baxter equation, which I did not write it here. But this is used for the coproduct on K. So the coproduct is almost, it's really almost co-commutative up to this R. So if you just flip the coproduct, then you get something which is the starting one up to this R. So this is, I will write here R and R bar to be R and its inverse. And in fact, to have a good representation theory, when you just act on product, you need when you act on product of object, you need, or maybe tensor product of linear spaces, then you need the coproduct in the algebra or in the Hopf algebra to bring things together. And so you have some compatibility condition between the coproduct and then these R. R13 here really means R on the first and then R on the last and then the identity in between. So because this object will be now in the threefold tensor product. You need to assume actually that it's triangular, otherwise things become so much more complicated. But then I will have what I will call braided Lie algebras. So braided means that you have a bracket, of course, but there is a braided anti-symmetry when you exchange the entries of the bracket. You just, apart from the minus sign, you get this R matrix. I mean, this is, R is in K tensor K, so I will write it as R alpha, meaning one is in the first leg and the other in the second leg. And there is also a braided Jacobi identity. So when you just pass through, you need to put R. Usually, classically, you will put a tau. I mean, the flip. Here, you need to put some R. So an object like that will be called a braided Lie algebra. If R is not triangular, but it's merely quasi-triangular, and nobody knows how to deal with these things here. It's really it becomes very, very complicated, and there is no good notion of Jacobi identity. Okay, so I will just take now the derivation of my bundle. See if again I will have this non-commutative principal bundle, and which is K equivariant. I will take the derivations which are braided with respect to this K. I mean, when I pass through, so U of A prime, this is U of A prime. So if R is the identity, this is the usual Leibniz rule. But I need now a twisted Leibniz rule. So again, I have to put this R matrix. And in particular, I will have those which are vertical. And this is a subalgebra of all of those. And again, I can think of these as infinitesimal gauge transformations in this non-commutative context. For the moment, it's just a name. But like I told you, I will have these to act on connections. So in this sense, I mean, there will be really a way to implement the gauge transformation when acting on connection. Okay, so here is the object that I'm then constructing. So these derivations, this equivariant derivation of the total space algebra, these vertical derivations, and there is this sequence which ends with the vector fields over the base space. So the derivations of the algebra of function on the base space. And this is exactly a version of the Atiyah sequence of a commutative principal bundle. In general, it's not obvious that this sequence is exact. So you have to check, and it need not be exact, in fact. So this object will be associated to a non-commutative principal bundle, which is also K equivariant. And a connection will be just a splitting of this sequence, a way to lift derivation for the base space into derivation of the total space, or maybe also a way to project here vertically. So of course it's completely dual. Either I lift or I just project them. And then of course the horizontal one will be the kernel of this projection, or maybe the image of this other splitting. Okay, so here is the structure. I can go, right? Yes. I have 5 minutes? No. Oh, okay, okay. Sorry. Okay. So here is the general structure. So G into P into T, and I'll need also an algebra. So all of them will act as derivations, braided derivations. And also I can multiply vector field with functions. So I have, first of all, this condition of braided derivation, and then this compatibility with the module structure. So B is the algebra of function over the base space. I can multiply vector fields with functions, and then I will have these things here. I mean, technically, this is called the braided Lie-Reinhardt pair. So rho is now a possible splitting. So I will just send element of T into P. And so I will, when I project back, I will have the identity. So this will be the lift of the vector fields or the vertical projection. So this will be a way to map a derivation from here down up here. And of course, they are just equivalent. You can give this or you can give this. There is the notion of a curvature. I mean, like classically, one way to think of a curvature is the fact that your connection fails to be a Lie algebra morphism. So the failure of rho to be a Lie algebra morphism is just your curvature. And then, I mean, you can also work out a kind of a structure equation. So your connection is really bringing up some kind of covariant derivative, and then your curvature is really the usual derivative of your connection, and then plus some commutator here. And there is also a Bianchi identity. So everything at least is consistent from this point of view. And that's the way I will act with gauge transformation. So I have my connection as my lift from T to P. And if I have any other map from T into G, then the sum of rho plus eta is still a connection. So as usual, the space of all connection is an affine space which is modeled on this G-valued one form on T, you could call. And here is a way, the natural way to act with vector field over your space of connection. You just take, essentially, just take the Lie derivative. And if you get vertical derivations, of course, this element is not there. And this is just the infinitesimal gauge transformation. So it's something that it's really, we know very well that this is the structure of an infinitesimal gauge transformation. What is really new here is that it was for a non-commutative gauge transformation and non-commutative connection is, the way to give this action is really very, very involved, if it's there, actually. Often it's not even there. And so here is just a natural way to give it. So I have a connection, I act on this connection via vertical vector field. And of course, there is also a transformation on the curvature. I need only 1 minute I have? No, I just want, okay. There is a cohomology. There is a cohomology which I will not mention. Always the information is in the cohomology. So there is a cohomology, but I just want to say that there is a cohomology and there is a cohomology, but there is also the fact that, there is a way to construct Chern-Simon terms. Oh, sorry, I'm a mess here. There is a way, somehow, you construct objects which do not depend on the connection at a cohomological level. And this object here is really the D of something, so the D of Chern-Simon term. To tell you, to show that this is not empty, this is the class of object that one can work with. I told you that this must be triangular. So these are the usual Drinfeld twist, or maybe this Jordanian twist. And so you can use this twist. But in particular, I will flash some example here on this theta force sphere. On this theta force sphere, and then you have a product, and then you have basic derivations, and then you have everything that you need for a calculus over S for theta. And, okay, so there is some SO theta 5 symmetry. And, but what is important is that there is a way to construct the sequence and to break it. So you can give explicitly an horizontal lift which breaks the sequence. And this is really a basic non-commutative instanton. In the classical version, this connection will be a way to give the connection one form of this splitting. This will be really a self-dual connection on S4, and maybe actually anti-self-dual, which is the first Chern class is equal to 0 and the second Chern class is equal to -1. So this is really an instanton. And there is an analog here, and you can, you can work out, the curvature, you can work out everything, you can work out the connection one form. The connection one form, which is anti-self-dual, like I said. And you can really also talk about conformal transformations, non-commutative conformal transformations, and then you can work out the action of this conformal transformation on this connection. This connection here is automatically invariant under SO5. The symmetry of this sphere. SO5 theta. so the deformed SO5 theta. But you have more room in SO51, and you get non-commutative families of instantons, and these families comes with five parameters, so a 5-parameter families of non-commutative instantons. So this is a way to put things in this context, and the theory is not empty. And of course, there is also beautiful. Sorry, I spoiled. There is in this non-commutative world, there are things which are not there classically. For instance, a non-commutative principal bundle over a point, which is from a commutative point of view is something trivial. But here, not. I mean, there are things which are classified by, for instance, H2. There are this worth of non-commutative bundle over a point. Or maybe there are there's this nice object, this Taft algebra, which is some kind of a truncated non-commutative torus. Then the non-commutative bundle over this Taft algebra are classified by C, so by a complex number. So it's something really very nice, even for these finite dimensional objects, something quite nice. Okay, I'm sorry, I was a bit, I was not giving much details, and maybe my slides were a little bit complicated to follow. But okay, so I worked out a gauge algebroid for a non-commutative principal bundle. Infinitesimal gauge transformations in this context. Well, I just only allude to the fact that I have a Chern-Weil theory and maybe Chern-Simon's terms. There is a lot of nice structures. There are many, many examples, and we're actually working out a class of examples on these deformed spheres. But I think at this point I should only say tanti auguri a Bal.
Do we have, I think people are anxious for coffee. So let's thank Gianni again. We should resume in 10 minutes, I think, just to try and get back on schedule.
I was on time, right?
It was, you were.
Yeah, sorry. Yeah,
It's okay.
I,
I was just checking.
yeah. I changed the
Oh, you did.
title. Yeah, I'll apologize for that. Yeah. Ah, there you are. Okay.
Okay, and the next speaker is Rajiv, who's going to tell us about matched pairs of Lie algebras in hydrodynamics.
Yeah,
So please.
Thank you. Yeah, I apologize for changing the title the last minute. I made the talk shorter, and so I changed the title to suit the topic. Yeah, so let me begin by thanking Bal for all these years of support and teaching me many things. In fact, I think I met you first in math science more than 40 years ago. Oh, Bangalore, yeah, that's right, yeah. That's right, yeah. I had some visa problems, and he was the one. So, happy birthday. I'll begin with that. So, I'll talk about an old problem in physics. In fact, I believe it is the oldest unsolved problem in physics, which is to understand the flow of classical fluids. So, this is classical in the sense that no quantum mechanics, no relativity. So, not only is h bar equal to 0 and c equal to infinity, even the speed of sound is infinite. I'll talk about very low speed flow. It is rather remarkable that this problem is still unsolved, and one manifestation of it is the phenomenon of turbulence, which is still unsolved. I'm not going to solve it today, but I'll talk about some mathematical ideas that may help towards understanding it in the future. So the overall mathematical framework is quite simple, and probably Euler had some inkling of it, but there's a whole family of physical systems which can be understood in terms of Euler equations. So Euler equations are differential equations in a Lie algebra. So given a Lie algebra and a metric on the Lie algebra, you have a differential equation. It's important that this is not an invariant metric. If it's an invariant metric, the whole thing is trivial. So I'll think about a metric in the vector space of the Lie algebra as a map, as a linear map, from the dual of the vector space to itself. So this is sort of like lowering an index. That seems like the most convenient way to think about a metric. So given a metric in the Lie algebra, it defines a Riemannian metric on the Lie group, which is left invariant, because the Lie algebra is the space of left invariant vector fields. And therefore, there are geodesics in the Lie group. And the differential equations for the geodesic on the manifold of the Lie group can be translated to algebraic equations for the tangent vector, more precisely the cotangent vector. And they are these equations. So the cotangent vector to the metric tensor is called omega, and the derivative of omega plus the nonlinear term that follows it is the co-adjoint action of g omega on omega. G omega is now an element of the Lie algebra, so it makes sense to ask how it acts on omega, and omega is an element of the dual of the Lie algebra, so that makes sense. So that is a nonlinear equation. Now, if there's an invariant metric on the Lie algebra, not all Lie algebras have invariant metrics, but if there is an invariant metric on the Lie algebra, then I can identify the algebra and its dual, and then the co-adjoint and the adjoint representations can be identified, and this equation can also be written in this way. So this is a little more elegant way to think about it. No. This is, it's not like torsion. It is just ordinary Riemann geometry. It's Riemann geometry without torsion that I'm talking about. Yeah. No, both are without torsion. Yeah, the entire thing is within Riemann geometry. Yeah. So the first example of this, yeah. If G is one, meaning if it is the invariant metric, then this vanishes. This commutator vanishes. And in that case, the solutions to the equations are one-parameter subgroups. In other words, the geodesics in the Lie group are just one-parameter subgroups. So the interesting case is the one where G is not invariant, and the solutions are more complicated. So the classic example of this, the one that Euler originally thought about, is the rigid body that we all teach in classical mechanics. So if you have a rigid body, then this omega is the angular momentum. The G is the inverse of the moment of inertia tensor. And so G acting on omega gives you angular velocity. So what this equation is saying is that the derivative of angular momentum plus the cross product of angular velocity and angular momentum is equal to 0. And angular velocity and angular momentum are related by the multiplication by the moment of inertia. So these are the famous Euler equations. I didn't write them down, but you can, I'm sure you've seen it in every book on classical mechanics. And these equations, Euler studied it, but they were completely analyzed by Jacobi years later. He solved it in terms of Jacobi elliptic functions. And it's a beautiful piece of mathematics. In fact, that work of Jacobi is the origin of the theory of elliptic curves, which nowadays is a fundamental part of much of algebraic geometry and mathematics. Now, Euler, independent of this, there is another set of equations in physics, also called Euler equations. These are the equations of an ideal fluid, an ideal incompressible fluid. There's the Euler equations of rigid body mechanics. There are the Euler equations of ideal fluids. The Euler equations for the ideal fluids, remarkably, is another example of exactly the same system. So these two equations of Euler from very different branches of physics are really two examples of the same fundamental idea. And he probably had some inkling of it, although at that time ideas like Lie groups and Lie algebras were not present. He must have seen that there is some connection between these two systems. So what is that? So here the equations of motion, so the fluid is incompressible, which really means that the fluid velocity is much smaller than the speed of sound. That's what incompressible means. So this condition here is the conservation of mass, that the divergence of the vector field is 0. And this here is the conservation of momentum. So the left-hand side is the derivative of velocity. I'm using units where density is equal to 1. So this is really the derivative of the momentum of a small fluid element. And that is set equal to the force on that fluid element, which is the negative of the pressure. Now, notice that there is no equation for pressure. That's because the pressure really is like a Lagrange multiplier that enforces the condition of incompressibility. So you don't really need a separate equation for pressure. There are 4 equations and 4 unknowns. So it is best to eliminate pressure from the problem, and you can do that by taking a curl. The curl of velocity is vorticity, this omega. And now using some standard identities of vector calculus, you can show that the nonlinear term here, after taking the curl, becomes the commutator of these two vector fields. The commutator is defined like this. The commutator vector fields in the usual sense of Lie derivatives. So the Euler equations of an ideal fluid can be written in this form, where I have the derivative of omega with respect to time plus the commutator of v and omega is equal to 0, and v and omega are related to each other by a linear differential operator, the curl. So this is exactly like Euler's equations for rigid body motion, Omega is analogous to angular momentum, v is analogous to angular velocity, and the differential operator curl is the analog of moment of inertia. So the entire story is very similar. In fact, this analogy is not a coincidence. A few years later, a few centuries later, Arnold in the 1960s showed that this also describes geodesics in the Lie group associated to the Lie algebra of incompressible vector fields. Incompressible means the divergence is 0. So if you have two vector fields whose divergence is 0, their commutator also has divergence 0. That's because the commutator in that case can be written as the curl of the cross product. So the divergence is 0. So this set of incompressible vector fields form a Lie algebra. The corresponding Lie group is the group of transformations that preserve the volume element. And the operation of taking the curl defines an inner product in the space of incompressible vector fields. So it defines a left invariant metric on the corresponding Lie group. And these equations describe the geodesics in that Lie group. So this is an observation of Arnold, and he used that to prove some results about fluid mechanics. So I've always been very impressed with this geometric interpretation of a very simple set of equations. These equations look extremely simple. In fact, I would say deceptively simple. Although the nonlinearity is just quadratic, we still don't understand these equations. For example, there is no theorem in mathematics yet that proves that these equations have solutions which are non-singular for all time. Although recently there has been some progress on it, and most likely there are singularities. It looks very likely that there are singularities. But I won't address that. That's considered one of the major unsolved problems in the theory of partial differential equations. The entire phenomenon of turbulence, which is still not understood, should in principle be a consequence of this rather simple set of equations. So it is worth studying these equations in some depth. They are at least as important to physics as, let us say, Young's theory or quantum gravity or problems of that nature. Oh, sorry, I somehow skipped ahead for a few. I don't know how that happened. Oh, I see. I am going the wrong way. That explains it. Okay. Okay. So the inverse of the moment of inertia is the thing that appears in the equation. The inverse of curl is a well-known Green's function, which I'm sure we have all seen. It's called the Biot-Savart operator. It appears in magnetism. The same problem appears in magnetism. Given a current, you have a magnetic field. The differential equation is the curl of the current is the magnetic field, is the Biot-Savart equation, and the solution involves this integral formula. So the operator G, what I'm calling G, which defines the metric in the Lie algebra, is the Biot-Savart operator. And quite a lot is known about it over the years. This problem arises in many places. So whenever you have a complicated problem, it's useful to study its lower dimensional analog. We don't understand turbulence in 3 dimensions, so we can understand the 2-dimensional case. Unfortunately, in 2 dimensions, the phenomenon of turbulence really doesn't occur. Even so, the mathematical structure can be understood quite well. I would say the 2-dimensional theory is fairly well understood by now. And the pioneering work is actually by Jens Hoppe, this man here. He has a PhD from MIT in '83, and his thesis had to do with membrane theory. And a big part of membrane theory is understanding the group of area-preserving diffeomorphisms. It plays a role analogous to the Verasoro algebra. And the way he studied it was, this was with Goldstone, was to somehow quantize that Lie algebra, and I will come to that. And then later he realized that this also has important consequences for fluid mechanics. And there's a very nice paper from 1993 where Hoppe explains this. So the key point is that in 2 dimensions, an area form, remember volume form in 2 dimensions reduces to area form. Area-preserving diffeomorphisms in 2 dimensions are the same thing as canonical transformations. In fact, an area form defines a symplectic form, And here is a fluid mechanics way to see it. This is elementary fluid mechanics. If the divergence of a vector field is 0, it can be written as the dual of a curl. And this is called, such a vector field has a scalar potential. This scalar potential is called the stream function in old-fashioned fluid mechanics books. Now, the commutator of two vector fields, which is again of 0 divergence, corresponds to some sort of a Lie product among functions, scalar functions. And if you look at it carefully, you will see that it is just a Poisson bracket. So the commutator of vector fields corresponds to Poisson bracket of the stream functions. This Poisson bracket says that the two coordinates x1 and x2 are canonically conjugate to each other. And then the Green's function of the, moreover, if you look at the vorticity, and you think about, the vorticity is a scalar in 2 dimensions, because the curl of a vector field in 2 dimensions is a scalar. So you get a scalar. So this scalar of vorticity is related to the stream function through the Laplace operator. So if you think of everything in terms of the scalar functions, the Green's function G that I'm talking about, the metric tensor in the Lie algebra, becomes simply the Green's function of the Laplace operator. It turns out that the correct boundary conditions are the Dirichlet boundary conditions. And the Euler equations become a set of differential integral equations for a scalar field omega, where this is the usual Poisson bracket, where x1 and x2 are canonically conjugate to each other. And this scalar function A is the Green's function of the Laplace operator acting on omega. So this is the way Euler equations look in 2 dimensions. And this has been very well studied. In fact, being a very old branch of mathematical physics, 2-dimensional fluid mechanics has been studied for centuries. For example, we can solve these by analyzing them in terms of a Fourier series. If you impose periodic boundary conditions in space, which is not very realistic, but it's a technical trick that is useful, then you can expand them in a Fourier series. The Fourier coefficients have to satisfy a reality condition. The Poisson bracket becomes essentially the cross product of the wave numbers. There's some typo here, but the cross product of the wave numbers. And in order to be able to solve Poisson's equation, the total vorticity must be 0. And then you can solve the Poisson equation, and the Euler equations become this system of equations. It's a system of differential equations for the Fourier coefficients. Now, I will illustrate in this 2-dimensional context essentially what Jens Hopper did, which is that for many purposes, for example, in developing a practical method for solving these equations numerically, it is useful to replace a system of partial differential equations by ordinary differential equations. So you would like to truncate the number of independent degrees of freedom to something finite. But this is a tricky thing to do, especially in areas like fluid mechanics, because if you take a Fourier series and you simply truncate it by cutting off the high-frequency modes, that doesn't work, because whenever you have nonlinearities, the product of two things with low momentum will go to the high momentum. So we understand this in quantum field theory. We have similar problems. So this is the problem of finding a regularization that preserves the symmetries of the problem, a gauge invariant regularization. In fluid mechanics, this is called the closure problem. The closure problem is that if you put a cutoff in the wave number, the nonlinearities cause higher harmonics that violate it. There is no elegant solution for this problem in 3 dimensions, but in 2 dimensions, there is a beautiful solution, and that's what Mr. Hepe was talking about. So what you do is you can impose a periodicity not only in position space, but also in momentum space. Now, this does not make much sense in terms of Euclidean geometry, but it makes sense in the sense of non-commutative geometry. Non-commutative geometry allows you to impose periodic boundary conditions not only in space, but also in momentum space. So if you do that, in 2 dimensions, there's a very elegant way to do that. And what happens is that the structure constants that appear here in the Poisson bracket, which was just P1K2 minus P2K1 is replaced, is deformed to this expression. In the limit as lambda goes to infinity, this reduces to the previous formula. Otherwise, it's not. But the remarkable thing is that this deformation still satisfies the Jacobi identity. That is the tricky part, is to find a deformation that satisfies the Jacobi identity. So this is called the sign Lie algebra. It appears in many places. So what is this Lie algebra? It's a finite dimensional Lie algebra. The dimension is of the order of lambda squared. It's actually lambda squared minus 1. And it is this algebra. It is a version of the unitary Lie algebra with a non-compact version of the unitary Lie algebra. So this corresponds to that. And the Laplacian 2 can be thought of as a finite dimensional matrix. Yeah, in the limit as lambda goes to infinity, it becomes the Poisson algebra that I had before.
Lambda plus 1.
Yeah, so in some sense, what I'm saying is that the group of canonical transformations is the limit as lambda goes to infinity of these non-compact unitary groups. So in the limit, it becomes the Lie algebra of canonical transformations. Now, of course, there are many different finite sequences, all of which tend to that same infinite dimensional algebra. This is one of them. The one that is appropriate for fluid mechanics is the non-compact unitary group.
Limit of UN, right?
That's right, yeah. So this is a non-compact version of UN. Yeah.
Could we use UN also?
So that depends on the precise context. In fluid mechanics, this is the proper way to think about it, yeah. That's right. So there's a very nice argument by Kaysen, Boris Kaysen, who is a student of Arnold, that shows that with this, it has to do with which reality conditions you impose on omega. Okay? The point is that there is the complex Lie algebra GLN. It has many real forms. Which real form you pick depends on the precise conditions you put on these coefficients f. So the... Huh? Oh, that's a technical trick. The point about lambda being odd is that then there can be a primitive unit of unity whose square root is also a primitive unit of unity. This is something you need in order to do this business. There's a similar thing when lambda is even, but it requires a little bit of a technical trick. So I use the particular regularization. Remember, these are regularizations, so this lambda is not supposed to have any intrinsic physical significance. You're supposed to let it go to infinity. So you pick one that is technically convenient. That's why. It has to do with roots of unity. I'll explain where the roots of unity come from in a minute. This has to do with the interpretation of this in terms of non-commutative geometry, which I won't go too much into, but that's where it comes from. So then this system of differential equations become finite dimensional. So instead of the structure constants are these functions A, and these are the modified versions of the Laplacian. And now these are fairly simple to solve. And this way you can see quite a lot of interesting phenomena about two-dimensional fluid mechanics. And by now it's a fairly well understood thing. By the way, this idea of Heppe has been sort of rediscovered by people in fluid mechanics about 10 years later. And they've got all kinds of prizes for it. But it is actually, I think, Heppe who did it first. It's a paper in Fissure of Letters, in fact, where essentially this idea is rediscovered. It's all part of the same idea, because that's also part of this non-commutative geometry. Yeah, that's right. I would like to generalize these ideas to 3 dimensions. That's really what I want to do. But before I do that, let me make a little bit of a digression make some technical comments about the 2-dimensional case. So there's a way to understand where this sign Lie algebra and so on come from. And you should think of it as a kind of quantization. Remember, I'm talking about classical physics with nothing quantum about it. But quantization can be thought of as a technical trick. Quantization in this context is regularization. It is a way of replacing the infinite dimensional Lie algebra by a finite dimensional algebra. So imagine that I could somehow take a compact phase space, which is the torus, and I could quantize that mechanical system then it is pretty clear that there is a fundamental minimum unit of length, which is something similar to this h bar. And there is, because the overall area of the phase space is finite, there are just a finite number of cells into which you can divide. And therefore, there are only a finite number of independent quantum states. Therefore, the quantum operators, the Hilbert space is finite dimensional, and the operators are just matrices. And so the quantization of such a system gives you matrices. And that's the way to understand what went on earlier. There's a more detailed way to do that. I found this in this paper of Kaysin, Lubashenko, and Raju. None of this is in the context of fluid mechanics, although Kaysin wrote a famous book on hydrodynamics with Arnold. It's the same Kaysin. So here, they describe how to do this. What you do is that you look at the canonical, the Lie algebra of canonical transformations, and you quantize it in the sense that you deform it by using not the usual notion of a derivative, but a deformed derivative. It is one of these Q derivatives, Q deformed derivatives. So this is the kind of things that many of you have worked on. And the point is that such a derivative satisfies a modified form of Leibniz rule, where instead of the derivative being satisfying the usual thing, this is sort of twisted by an automorphism of the algebra. And now you take any function on the phase space, I can turn it into a pseudo-differential operator of this kind. And then there's a very nice calculus for such pseudo-differential operators, which is the Q analog of the Gelfand-Dickey symbol calculus. And so using all this, you can give a precise justification for that sign algebra trick. So I just wanted to mention this to place it more in the context of this conference. Okay. Now, what I really want to do is to generalize all this to 3 dimensions. And immediately you can see there's a problem. You can talk about 3 dimensions. You cannot have a symplectic form in 3 dimensions. So it cannot be that obvious. But here is sort of halfway there. So it's useful to study an intermediate problem before looking at the full 3-dimensional case. Let's consider incompressible vector fields in 3 dimensions. It has 2 independent degrees of freedom, because you have 3 components and 1 condition. It has 2 independent degrees of freedom. Let's cut the degrees of freedom in half by requiring, in addition, that the vector field preserve a scalar field alpha. This alpha is somehow arbitrarily picked. It is like one of the coordinates. Okay? So it is a function without critical points, meaning that the gradient of alpha should be non-zero everywhere. So there is a subalgebra of the Lie algebra of incompressible vector fields, which also preserves alpha. This simply means that the derivative of alpha along U is equal to 0. It is clear by construction that this is a Lie algebra, because it preserves the density, it preserves alpha. So I call it 2.5 dimensional, because it's sort of halfway between 2 and 3 dimensional. Now, such a vector field, which preserves both the volume form and alpha, can be written as the cross product of the gradient of alpha and A. This may look like a Klebsch decomposition, but I'm holding this alpha fixed. Alpha is fixed. So every vector field of this kind is of this type. Now, if you take the commutator of 2 such vector fields, that corresponds to a Poisson bracket on these scalar fields. So that is reminiscent of what happens there. This Poisson structure is defined in terms of this alpha. It depends on alpha. But it is not a symplectic form. It is a Poisson structure. And it is only in the surfaces where alpha is a constant, where that is a symplectic form. The surfaces where alpha is a constant are the symplectic leaves. So there is a Poisson bracket. So this is a 3-dimensional analog of the story that we already had in 2 dimensions. But this is not enough to do fluid mechanics. I think I talked about this. This is not enough to do fluid mechanics. There is no fluid mechanics in 2.5 dimensions. Because remember that in addition to the Lie algebra, we also have the curl operator, or the inverse of the curl operator. The curl operator is not closed in that subset of Lie. So you have a Lie algebra of vector fields that preserve alpha, but the curl of that no longer preserves alpha. So you cannot do fluid mechanics with it. And that's easy enough to do by a short calculation. So we cannot do it there. So we really have to study both components of the vector field in order to study fluid mechanics. So this is something that people have studied. It's an old subject, so these ideas go back. So already in the 19th century, Klebsch and contemporaries produce various parameterizations of incompressible vector fields in terms of pairs of scalar fields, none of which, they're all quite complicated. The Klebsch parameterization, for example, is highly nonlinear, and it doesn't quite fit the kind of ideas that I'm talking about. There's something called the toroidal poloidal decomposition, which you'll find in papers of Chandrasekhar. So there's a long literature of it. But I propose in an earlier paper that we do this simple decomposition. That is, we do exactly what I said a minute ago, but you do it twice. So there is one set of vector fields which preserve some scalar field alpha. There is another set of vector fields that preserve another scalar field beta. Alpha and beta are independent of each other in the sense that their gradients have non-zero cross product. So they point in different directions. So they're independent in that sense. Every vector field which is incompressible can be decomposed in this way, and A and B are the two independent scalars. Now I'm cheating a little bit because there are a finite number of degrees of freedom associated with non-trivial cohomology. If the space we are talking about is not simply connected, there are some harmonic things you can add. I'm ignoring that, except for that. So every vector field can be decomposed in this way. Now, each piece describes a subalgebra because the vector fields that preserve alpha form a subalgebra, the vector fields that preserve beta form a subalgebra. So the situation we have is that we have a Lie algebra of incompressible vector fields. It has two subalgebras A and B, and as a vector space, S is the direct sum of A and B. Any element of the big Lie algebra can be uniquely decomposed as a sum of something in A and something in B. But here's the most important thing. This does not mean that this S is a direct sum of A and B as a Lie algebra. It is not. As a Lie algebra, it is not the direct sum. It is not a semi-direct sum either. Because although A and B are separately subalgebras, neither one is a normal subalgebra. So this is very different. So for example, if you look at the Poincare group, Poincare Lie algebra, the Lorentz algebra is a subalgebra. Translations are a subalgebra. But translations are, in addition to being a subalgebra, translations are also an ideal, meaning that even a rotation acting on a translation gives you a translation. So such a structure does not exist here. So this S is not a direct sum. So it is mathematical literature. This is denoted by this bow tie symbol. B and A act on each other. Okay. This is called a matched pair of Lie algebras. So we can study, and there is some literature about this in the mathematics literature. Suppose I am given two Lie algebras, A and B. How can I combine them to get a bigger Lie algebra S? Without assuming that A and B, that either A or B is an ideal of S. What conditions do you need? The necessary and sufficient conditions are called the matching conditions. So suppose I know the commutation relations in A, commutation relations in B. Now, what is not determined in S are the mixed brackets of A to B. So the bracket of something in A with something in B can be uniquely decomposed as something in A plus something in B. Therefore, it determines a pair of quantities, B acting on A and B acted upon by A. And the question is, what are the conditions to be satisfied by this pair of operations? And it turns out that these are the four conditions that must be satisfied. They're called matching conditions. Yeah. That's exactly what it is. That's right, exactly. This is the Lie algebra version of the bicross product. Yeah.
So what happens to the coproduct to the Lie algebra?
Yeah, we don't need the coproduct here because I'm not talking about a Lie bialgebra. This is just a Lie algebra. I'll come to the connection to Lie bialgebras in a minute. Okay. Yeah, so this idea has been discovered and rediscovered repeatedly in algebra, and it really, I think, goes back to Zappa in the context of groups. So Zappa discovered exactly the analog of this idea with groups. So you have two groups, how do you combine them to get a bigger group? So this bicross product, this is called the Zappa product. It was rediscovered by Takeuchi in the context of C-star algebras. Takeuchi. It is all in that context, that's right, yeah. So then eventually it was taken over to Hopf algebras. That's right. It turns out that the Lie algebra version is a lot simpler than all of that. So I'm describing it in the language of Lie algebras. That's right. So the Jacobi identity requires these conditions. These conditions are exactly what you need to satisfy the Jacobi identity. That's right. These 4 conditions are necessary and sufficient for the Jacobi identity to hold. Well, you know, any Lie algebra defines a Hopf algebra. Beyond that, you don't need the Hopf algebra. This is why I think it is easiest to understand it in the context of Lie algebras. No. These are all rather trivial Hopf algebra. These are co-commutative Hopf algebras. Because any Lie algebra defines a co-commutative Hopf algebra. So the most famous examples of matched pairs are Lie bialgebras. So the most famous examples are when these A and B are of roughly equal size, and they are dual to each other with respect to an inner product in S. In that case, it is a Lie bialgebra. But that's not necessary. The idea of a matched pair of Lie algebras is more general than the idea of a Lie bialgebra. So I'll give here an example, which I think is an elementary example, which is an example of a bi-cross product of Lie algebras, bi-cross sum, I should say, of Lie algebras. And it is this. Take the Lie algebra of m plus n by m plus n matrices, GL of m plus n. It has a subalgebra consisting of matrices of this type. So the A0 is an m by m block, A1 is an m by n block, while B consists of an n by n block and an n by m block. So you can see that the product of 2 matrices of this type is again of that type. Similarly for B. So separately they are Lie algebras, Lie subalgebras. The intersection is trivial. Only 0 is of both types. So GL m plus n is a direct sum as a vector space of matrix of this. Any matrix can be uniquely decomposed as something of this type and something of this type. And separately, they are subalgebras. So you can ask, this must therefore be an example of a matched pair, and a short calculation will tell you that the action of B on A is given by this formula, and the action of A on B is given by this formula, and that they satisfy those conditions. So notice here that there is no reason why A and B should be of the same size. The dimensions of A and B are not necessarily equal. For example, M may be very different from N. But the most famous examples of this structure are the cases where A and B are of the same dimension, or more precisely that they are dual to each other as vector spaces. In that case, these are Lie bialgebras, and this is an example in that case of what is called a Manin triple. But my point is that you don't need that. This idea is very general. So I think this is a very useful thing, because how do you study complicated groups or Lie algebras? You break them up into smaller things. Usually when you break them up into smaller things, each piece, at least one of the 2 pieces is an ideal. So for example, in Wigner's theory of representations of the Poincare group, he starts by studying representations of translations, and then he looks at the action of rotations or Lorentz transformations on translations. So they're using the idea that the translations form an ideal. But this point of view here, because you don't require the 2 pieces to be ideals, they also apply to simple groups. So simple groups don't have ideals. How do you break up a simple thing? The whole idea of a group being simple is that you cannot break it up into smaller things. You cannot break it up as long as you insist that each piece is a normal subgroup or an ideal. But here you don't have that. So in fact, there is some very nice body of work on groups by Agore and collaborators. Oh, okay. Okay, so I used too much of my time. Okay, so now we can apply these ideas to 3-dimensional fluid mechanics. Okay, so I've introduced the basic ideas. So what we have is that So what we have is that we can take a vector field that is incompressible, decompose it as a sum of 2 terms, one belonging to each subalgebra, and then you can verify that there is an action of one on the other. So we can translate the commutation relations of vector fields to some sort of Poisson-like brackets on A and B. In fact, among the bracket of two things like A and two things of type B indeed are Poisson brackets. So the question is, what is the bracket of something of type A with something of type B? And that involves one of these actions of B on A and A on B. These subscripts correspond to differentiations. B2 means differentiate with respect to the second coordinate. So I'm using a coordinate system in which alpha is a second coordinate and beta is a third coordinate, and the remaining coordinate is along the cross product. There's always such a unique coordinate system. And you can work out that this is the Lie algebra of incompressible vector fields written in terms of these scalar fields, written in this language. Yeah, so you just need to add a boundary condition of some sort. Yeah. For example, yeah, we can use Fourier transforms. Yeah. If you have periodicity, you can impose Fourier transforms. But that's not always the most physically correct boundary condition. But you need some boundary condition. Yeah, in fact, there's a whole story about boundary conditions in fluid mechanics, which is much like the story of boundary conditions in quantum field theory. Yeah, yeah. There's a whole theory of that. Okay, again. Yeah, so the other ingredient is the curl. So you can work out the curl in this language as well. And the curl is a sort of a 2x2 matrix of differential operators. So it's a short calculation to work that out. The inverse of the curl you can work out also. And now we have all the ingredients to write Euler's equation in terms of the scalar potentials. So we can take the vorticity. We can decompose the vorticity into a part that is within the subalgebra A, within the subalgebra B. And if you write it out explicitly in terms of coordinates, it looks like that. The second and third components involve only differentiations along the first coordinate, and then this has to do with the remaining differentiations. And now the velocity, which is the inverse of the curl, you have to actually calculate out. And so the scalar potentials of velocity are related to the scalar potentials of vorticity through this integral operator. So this thing here is the Green's function of the Laplacian, and so on. So it's a fairly straightforward thing. And you combine all this, and you can indeed write Euler equations in this way. So the first part of what I described, that the equations of two-dimensional fluid mechanics can be written in terms of some Poisson-like brackets and curl, can also be done in 3 dimensions. And this is fairly straightforward. This is not, so the important thing here is that this does not assume anything special about the vector fields. This is just the most general case. Okay. Now, what would you like to do with this? So one thing I would like to do, which I haven't been able to complete yet, I think it's a fairly difficult problem, is how do you regularize this problem? This is the fundamental problem that I would like to accomplish. This is an old problem in fluid mechanics. It has been with us throughout the entire history of fluid mechanics for the last 250 years. It is called the closure problem. How do you truncate this infinite dimensional system of differential equations to something finite dimensional without doing violence to the underlying symmetry, which is the Lie algebra? How do you replace the Lie algebra by something else? The difficulty here is that these Lie algebras are in some sense rigid. There's no way to deform them without somehow destroying the commutation relations. The hope is that you can deform them if you don't insist on them being Lie algebras, but something in a more general category, for example, Hopf algebras. Although they cannot be deformed within, so in the two-dimensional case, we could deform the Lie algebra of canonical transformations and replace them by another Lie algebra, which is this Lie algebra of unidot transformations. That may not be possible in higher dimensions. And that is the direction I would like to go with this. So this is the idea of quantization as regularization. So it turns out that quite a lot can be done. I didn't want to write out long, complicated formulas. These ideas about taking a function. So what happens is that if you have a function of 3 variables, as far as A is concerned, x1 and x3 are canonically conjugate. As far as B is concerned, x1 and x2 are canonically conjugate. Therefore, I can turn A into a zero differential operator and B into a zero differential operator. And now the tricky part is to translate those matching operations. How does A act on B and how does B act on A? The product of B times A has to be rewritten as the product of the type A times B. And there is a way to do that using this simple calculus. And they lead to very complicated formulas, which I didn't want to write down. And if one can work this out in principle, I believe that there is a solution to this closure problem within this context. And the way things become finite dimensional is that this deformation parameter Q, when it is a root of unity, things simplify to a finite dimensional case. And it is this Q being a root of unity is where this odd, it is an odd root of unity. It is a root of unity of odd order. That's a technical simplification because in that case, the square root of Q and the square of Q are also primitive roots. So let me stop here. I'm happy to answer questions. Yeah.
So in the example of quantization that you briefly mentioned,
Yeah.
if you quantize the phase space,
Yeah.
then and for instance, if the phase space is, the manifold is finite, is finite in size, so to speak, then you get cells, right?
Yeah.
And there is we know the meaning. We have a physical meaning for that finiteness because
Yes.
there's an underlying fundamental constant that emerges, which is h bar.
Yeah.
So, in the kind of examples that you've been looking at, is there a similar fundamental constant that might emerge for?
So here, remember, quantization is just a technical tool.
Right.
Yeah.
But then
So
the fundamental
that
constant.
lambda that I mentioned is
Yeah.
essentially 1 over h bar.
Okay.
So lambda going to infinity is the limit when you remove, that's why I called it lambda, because it's a cutoff. When lambda goes to infinity, it's as though h bar goes to 0. In fact, in a rather precise sense, lambda is exactly, essentially 1 over h bar. Q to the power lambda in this deformation business is equal to 1.
Okay. Well, I was wondering whether there were more interesting length scales that might emerge which have...
So, of course, I have an ulterior motive in doing this. I think that simply by studying old-fashioned subjects like fluid mechanics and trying to solve problems there using these ideas, we will learn something about how to do it in a fundamental theory also. So perhaps one message that I can say is that this story gives you a natural way of trying to construct diffeomorphism groups in higher dimensions in terms of diffeomorphism groups in lower dimensions. So remember I said here that the diffeomorphism group of 3 dimensions can be decomposed into 2 pieces. Now each of these pieces is essentially 2-dimensional because it is a direct sum of 2-dimensional canonical transformations on each surface where alpha is constant. So the diffeomorphism group in 3 dimensions, although it is intrinsically 3-dimensional, is the bi-cross product of 2 pieces, each of which is essentially 2-dimensional. And this construction essentially carries over even to higher dimensions. So for example, and it doesn't even require the condition of incompressibility. If you look at the Lie algebra of all vector fields in 3 dimensions, it can be broken up into 3 pieces. Each one is essentially 2-dimensional, and so on. So I think that one lesson you can get from this is an approach to constructing things like theories of quantum gravity, based on this idea of decomposing it into lower dimensions.
Yeah, can I ask one? So in Hoppe's approach, when you regularize that, you're replacing the diffeomorphism group with a unitary group.
Yes.
But diffeomorphism groups are intrinsically very different because the Lie algebra, it doesn't exponentiate to the group. So
Yeah. By the way,
is there some way of
yeah.
understanding that you're recovering that in the limit?
So the idea is that the regularization has somehow tamed that problem, but that problem will reappear in the limit in some way. Yes. Maybe that's what you mean. That's right.
But will it reappear in the limit? Or are you really losing that?
Yeah, I think it will reappear. In fact, there's a lot of nice work by Kaysen. That's what he has been working on geodesics, on diffeomorphism groups. And there are a lot of these phenomena that are sort of intrinsically infinite dimensional, which of course will not happen once you impose the regularization. But at least some of them I can see how they reappear. Okay? And I would say that these are analogs in fluid mechanics of what we call anomalies in quantum field theory. They are this phenomenon you're describing is analogous to an anomaly in quantum field theory. Of course, once you have a regularization, you no longer have an anomaly, but we understand how they appear in the limit. So this is an example of that kind of phenomenon. They're related to things like index theory, by the way. This thing that you mentioned is related to the index of some differential operators. So it's very much like the theory of anomalies. I think that's an interesting thing to study. Basically apply our knowledge of quantum field theory to these kinds of issues. Yeah.
I had a question. So in the previous case, when you had alpha, when you had the Poisson manifold, could you not just worked with Poisson manifolds and done some deformation quantization?
Yeah, so you can do that, but you'll only get half the story. You'll only get that A part of the story. Okay, you will not get the other part. So my idea essentially is that although the three-dimensional space being a Poisson manifold doesn't recover the whole set of vector fields, each piece is a Poisson manifold, and there is this way of putting them together.
I see.
So this trick of combining two Poisson-type Lie algebras will reproduce the entire thing.
So
that's the new idea here.
With this new parameterization, you still have a Poisson manifold structure?
Each piece is separately a Poisson.
And this bialgebra you got is like...
But once you take the by-cross product, it is no longer a Poisson.
It's
type.
not a Poisson.
No, it's not. That's very important that it's not. Yeah.
So we can't do deformation quantity.
No. Yeah, that's right. We can do that. By the way, what I'm doing is basically that for each piece.
Yeah.
Okay. So my idea is to take this concept of deformation quantization for each piece and then combine them. And the whole intricacy is in how you combine them. That's where the whole thing happens.
Can I ask a question? Yeah. I'm a bit puzzled about the fact that three-dimensional diffuse can be constructed from 2D.
Yeah.
Because there are, for example, uncountably many three-dimensional manifolds. That is not the case with 2 dimensions, which are all connected subs, like orientable 2D. They are all connected subs with tori. Okay?
I don't know the answer to what you're asking, because all my considerations are local.
Are local, no?
Yeah.
That's what I wanted to know.
Yeah. So I have not really seriously studied what happens at the level of the complete manifold. Everything I'm doing is within some, remember I was using specific local
So you're
coordinates.
using the fact that
everything is local.
Locally R3.
That's
locally they are different.
That's right.
Okay.
So everything I'm doing is local.
Yeah. What happened to that work called Manin triple that you were telling before?
That's a particular case of this. Okay, so I didn't mention this. So my point here is that this is a by-cross product of Lie algebras is a more general idea than Lie bialgebras. But if you have an invariant inner product with respect to which A and B are dual to each other, it reduces to a Manin triple. Okay. So a Manin triple is a particular case of a by-cross product.
Oh, I see.
Okay. And that particular case happens to be what is relevant for fluid mechanics, because in fact, this fluid mechanics has an invariant inner product.
You need isotropic.
Which is called helicity.
Isotropic.
Yeah, that's right. But I wanted to de-emphasize that part, because I believe that this concept of by-cross product of Lie algebras is more general and more useful in other areas.
Let us thank Rajiv
thank you.
again, because we should move to the next speaker. Oh, sorry, you have a question? Yes, speaking. Yes, that's what I thought.
change the page? I don't need to, okay. Change the page. How? Okay.
So the next speaker is Narayan, and he's going to tell us about heterotic strings.
Right. First of all, let me just say a few words, since this is BalFest, a few words about my experiences with Bal. So, I mean, I joined Syracuse in '76. That year, Bal was on a sabbatical to India, in fact, the whole year. But then, okay, I met him after that, after 1 year. And then there were these brilliant students of Bal who joined. First was Parameshwaran, then Rajiv, then Fidele, and it was and the thing that I remember most was, even though I was not Bal's student, they used to have discussions almost after lunch, almost every day, and he would also knock my door, ask me also to join, and it was really a great learning experience for me, just to sit there and listen to these brilliant discussions, So I really learned a lot from those meetings, yeah. And of course, I should also mention so many evenings I spent at Bal's house and had South Indian food with Indra and okay. So I'll try to be very, very brief because I think we are over time. And yeah. So the topic that I'm talking about is string theory, which is, I think, a bit outside this meeting. So what I'll be talking about is heterotic strings compactified on T3 mod Z2, and compare it with the M theory compactified on K3, where you have a Nicolin involution on K3. Okay, Z2. I'll be only considering Z2 involutions. Okay. So first of all, let me see. This work was done in collaboration with Bobby, Gerardo Aldazabal, Ana Maria Font, and Aida Zadeh. And this appeared in the JHEP. It's a long paper, but this talk will be very, very brief with no mathematical details, just basically qualitatively describing what was happening. Okay. So M theory compactified on K3, this is a kind of known fact, that M theory compactified on K3 gives a 7-dimensional theory with 16 supercharges. And the rank of the gauge group is 19 plus 3. And this comes from the 3-form fields expanded in terms of the 19 anti-self-dual and 3-self-dual 2 forms, okay, on K3. Membranes wrapped on the 2 cycles of K3 are charged under these gauge fields, and these charges span a lattice gamma 19,3, which is even and self-dual, okay, with the Lorentz signature 19,3. Right. The heterotic dual of this theory is simply a T3 compactification of the 10-dimensional heterotic string, and combining it with the, so this is obtained by compactifying on T3 and combining with E8 plus cross E8, or one gets a charge lattice of 19,3, which is even and self-dual with Lorentz signature 19,3. So this is the way the identification works on the 2 sides. Okay. So now we're going to consider non-supersymmetric orbifolds of heterotic string T3 obtained by reflection on 2 of the 3 right-moving directions. So remember, in heterotic string, you have the left-moving sector and the right-moving sector. Left-moving sector is a bosonic string, which is a critical dimension of that is 26 dimension, and the right-moving string is a fermionic string whose critical dimension is 10. No? This is combining this. So from this, the fact that there's a 26 on the left and 10 in the right, there are 16 directions which are purely left-moving. Okay. So it's a kind of asymmetric, I mean, you have string theory. Okay. So now what we're doing is that we want to consider heterotic string and consider a Z2 orbifold, non-supersymmetric orbifold of heterotic string obtained by reflecting 2 of the 3 right-moving directions. Right-moving, these are the fermionic directions, fermionic string directions, and S of the 19 left moving directions. So these are the Z2 asymmetric orbifold. Okay. Actually, we'll see later on that Z2 is always automatically promoted to Z4. So, but we would expect these models to be dual to M theory on K3 modeled by Z2 involutions that acts on the membrane charge lattice. Okay. This membrane charge lattice, as we mentioned, is gamma 19,3. And this Z2 involution that I'm talking about in the heterotic string is exactly acting on the gamma 19,3, right? So, so what are these Nicolin involutions? These are the involutions on K3 that leaves a Kähler form invariant, but gives a sign to the holomorphic 2 forms. Okay. And this has been classified by Nicolin in 1980 in terms of the sublattice I of gamma 19,3, which is invariant under the involution. Okay. So the sublattice I, what I mean by that is a sublattice of 19,3, which is invariant under this Nicolin involution. So this classification is given by 3 numbers, R, A, and delta, where R is the rank, is a dimension of I. Okay, R is a dimension of I, which has signature R minus 1, comma 1. Okay. Why is it R minus 1, comma 1? Because as we said, we are looking at, on the fermionics side, we have just 2 reflections. Okay, so that leaves still 1 direction left over, and the remaining R minus 1 comes from the anti-self-dual forms. And the number A is defined by I star over I. Okay, I star being the dual lattice to I. Okay. So it is the order of this I star divided by I. So remember, because gamma 19,3 is self-dual, the invariant sublattice will be an even integral lattice. Okay, not self-dual necessarily. So it will be even an integral lattice. The dual lattice, therefore, will be, the I lattice will be contained in the invariant, in the dual lattice. I star, I is contained in I star, and this 2 to the A is simply the I star, the order of the I star over I. Okay. So that is the number A. And delta, finally, delta is just 0 or 1. When delta is 1 when the I stars have integer length squares. Okay. You see, the fact that I is integral, and you can immediately deduce that this I star, length squares of vectors and I stars are either half integer or integer. Okay. So what this condition is saying is that if it is integer, then delta is 1, otherwise delta equal to 0. Okay, that's a classification given by Nicolin. So we denote by n the sublattice of gamma 19,3, which is orthogonal to I, and therefore has dimension. How do I go to the next page? Page down. No, yeah. So this table summarizes the Nicolin's classification. Okay. So here on the horizontal axis is R. R is the same as 20 minus S. S is the number of directions one is reflecting. And A is the number that I mentioned, I star over I, order of the I star over I. And delta equal to 0 and 1 are denoted by, delta equal to 0 is a blank circle, and delta equal to 1 is the other one. So there is the black spots. So that's the classification given by Nicolin. And what our aim is to look at the heterotic string constructions and obtain all these points. Okay, that's our aim. Page down. Okay, so idea here is to so in heterotic string, as we mentioned, there is we basically reflect. We do a Z2 reflection on 2 of the right moving directions, and R minus S minus S of the S minus 2 of the left moving directions. So this is the thing. So to understand this construction, it is more instructive to look at just to look at SU2 flat connections on the T3. Okay? Because remember, heterotic string is compactified on T3, and even though the gauge group is E8 cross E8, it is better to first look at the SU2 and see what happens. What are the different sectors that you can write down? So T3 coordinates, we just write them as x1, x2, x3, 3 Euclidean coordinates, which are, of course, periodic. This equation number 1 just gives the generators, xi going to xi plus 1. And in order to have a T3 over Z2, we have also a fourth generator, which identifies these points, x1, x2, x3, to minus x1, minus x2. And I'm considering here a freely acting orbifold, so I have just shifted the x3 to x3 plus half, although it's not necessary. When we discuss string theory, we don't need to really talk about the freely acting. This is just to understand in a field theoretic language. Okay, so the fundamental group can be described abstractly in terms of these 4 generators, Gi and G theta. Gi are the standard generators for the torus, and they are obviously commuting with each other. Gi Gj is equal to Gj Gi for all I 1, 2, and 3. And the fact that G theta is a reflection of the x1 and x2 directions, it gives us this formula that G theta G1, G theta inverse is G1 inverse, right? And similarly for G2, whereas G theta does not do anything to x3, it only does a shift, okay? So the fourth equation is without, I mean, the right-hand side is G3 again. And finally, G theta square is equal to G3. That again one can see from the equation number 2. Okay. So this is the abstract relation between these generators. And now, what we want is to look at all the possible flat connections on the heterotic string, E8 cross E8, or spin 32 over Z2 gauge bundle. So these are specified by some Wilson lines. And these are one for each generators, obeying these relations. Okay? So we want to map these G's into the gauge group, okay, which satisfy the same relations. Okay. So there are two types of solutions one can write. So here we are again looking at SU2 for the time being. Then once we understand SU2, we can extend it to any of these Lie algebras here. So one of them we call Higgs branch, and we can write this as, so G1 is some generator, some group element along the third direction, sigma 3. G2 is again in the same. And G theta is I sigma 2. G3 is minus 1. Okay? This is the Higgs branch solution. One can verify that this choice satisfies all those equation number 3. Note that G theta in those solutions satisfy G theta to the 4 is equal to 1. So it's really a Z4. This solution can be easily generalized because anyway you can decompose E8 cross E8 or spin 32 over Z2 in terms of SU2 to the 16. No? So we can just take 16 copies of SU2 and put this, generalize it. Now these solutions have a moduli space which is, page up here. You see here that phi1 and phi2 are continuous parameters. So these are the moduli. Okay. And so these have a moduli space. Which are parameterized by phi1 and phi2. Hence, the low energy effective field theory will contain 2 light scalars, which will naturally form a complex scalar field. And at the origin of the moduli space, when phi1 and phi2 are equal to 0, then there is an SO2 subgroup of SU2, which commutes with the flat connections. So these are the SU2 matrices with real entries. Therefore, the 7-dimensional theory has an enhanced SO2 gauge symmetry at that point, okay, which is broken for generic values of phi1 and phi2. So that's why we call it Higgs branch. So by giving wave to phi1 and phi2, you are breaking the gauge group. I mean, breaking the rank itself. So that's one branch. Other is a Coulomb branch solution. And these solutions are, can be described in the following way, right? G1 and G2 are mapped to identity. J theta is some element in the U1 subgroup generated by sigma 3. And G3 equal to J theta square. Okay? So this is a Coulomb branch. Okay. One can easily see that this doesn't break the gauge group. Okay. That's the Coulomb break. Okay, we can extend this to any gauge group as we mentioned before in terms of for the E8 cross E8 or also 32. Now one thing that one should notice, and this plays an important role here, that if you go back to the Higgs branch solution, right, no, this is not, I should go up, page up, yeah. Yeah, if you look at the Higgs branch solution, and if you set phi1 and phi2 equal to 0, and just instead of G theta being equal to I sigma 2, you rewrite it as I sigma 3, which can be done by just the group rotations, right? You arrive at, again, the Coulomb branch solution. No? So at the point phi1, the 0 values of phi1 and phi2 of the Higgs branch, there is an intersection. These two branches intersect at some point. So this will be an important thing because we'll be able to make transitions from the Higgs branch to the Coulomb branch by going to that special points. And this way we'll be, in fact, able to connect all the different Nicolin points, which you don't see in the M-theory language, but in the heterotic side, these transitions will be quite easy to understand. Okay. Now returning to the asymmetric orbifold of heterotic string on T3, where now we do not necessarily restrict to the freely acting orbifolds. So I will not give any details here, just basically summarize the various points here. So first of all, what is the group action? It is on the right movers, as we said before, right movers, which means fermionic string sector. The G acts as a rotation by pi on a two-dimensional plane. Thus, G square acts as -1 on the space-time fermion, right? Because this rotation, G square is rotation by 2 pi, but on the fermions, it acts as -1 space-time fermions. And therefore, really, this G is of order 4. So this is a Z4 orbifold, actually. This would not have been the case if we had rotated 2 planes, like in order to get, for example, K3 orbifolds. That would not have been the case because you're rotating 2 planes by 2 pi. So fermions come back with a plus sign. No? But this one picks up a minus sign. So it necessarily becomes Z4. Okay, in general, we may also include some shifts in the definition of G, that is, which acts on the states P carrying the lattice momentum P. I mean, of the E8 cross E8 or SO32 over Z2, spin 32 over Z2, the charge momentum P. Yeah. So it can act also, apart from this rotation, it can also have that action. Okay. More generally, when the lattice vector P belonging to 19,3 has components along both I and N directions, then G will act in the way shown in equation number 6. So Pn and Pi are so P is a vector, and Pn or Pi are the components along the N directions and I directions. So I directions, again, remember, it is the invariant directions under the rotation, and N directions are the normal directions to that. So P under the action of theta, Pn Pi goes to minus Pn comma Pi, and G acts as given in equation 6. So from equation 6, if you take G square, you get equation number 7. And now you see Pn Pi is mapped to the Pn Pi. So this product Fpn times F minus Pn times this e to the phase factor altogether will be some phase, be plus or minus 1. Because remember, we are talking about Z4. So G square should be plus or minus 1. Okay. It turns out, and I won't describe this, why that is the case, the natural choice is Fpn, F minus Pn is equal to e to the power of 2 pi I Pn square. And this actually follows from the discussion of the Higgs branch and the Coulomb branch. Because in the Higgs branch, the way I had defined the Higgs branch, what happens is that on the root lattice of SU2, it acts as a +1, G square acts as a +1, whereas in the fundamental conjugacy class of SU2, it acts as -1. Okay. And that's exactly the condition given here. Now, one loop modular invariance. This requires a lot of the string technology. So I will just state the result here. So what happens is that in string theory, maybe I just mention. Can I use the blackboard? Okay. So if I look at the string world sheet, at one loop level, that's torus, right? That's a T2, and it will have 2 cycles. So one of them, let me call it sigma direction of the string, the spatial direction of string, 2-dimensional, and T is the time direction, the world sheet time, okay? And this is the torus, so these are both our cycles. So if I want to write down the partition function, so now we want to write down the partition function for G invariant states, right? G is this orbifold group element, G. So G invariant states, well, then that's nothing else but the trace over the Hilbert space of the original string theory. And you have 1 over n divided by 1 plus G to the power of n minus 1, right? In our case, n is 4. Sorry, this n I shouldn't confuse. So let me just write explicitly just that. Okay. This n I should not confuse with that n lattice, Okay. So this is so I have to compute the trace of this times, of course, q to the power of L0, q bar to the L0 bar. No, this is the partition function. But insertions, in the usual theory, without doing any orbifolding, it would be simply identity here, and that would be the case, right? But now what we want to look at is the partition function of G invariant states, so I have to apply the projection operator. Right? But at the level of string, at the level of this the path integral formulation, what this G means is that I look at the same diagram, sigma t here, except that here I twist by G. Okay? So as I go from, because the G action in the path integral language will, when you evolve along the time direction, it comes back here by twisting by G. No? So you get all these sectors here. So 1, 1, plus this, plus G square 1, etc. All of these sectors. Okay? So that is what gives the partition function of the G invariant states in the original Hilbert space. But now, if I just stop here, this will not be a consistent string theory, right? Because the string world sheet has this SL2Z, PSL2Z modular group. So a particular element of this group is exchange of the 2 cycles. No? This means that in order to have modular invariance, I must include also a diagram like G1. No? This is a new Hilbert space. This was not there in the original string theory. So these are called the twisted Hilbert spaces. Twisted Hilbert spaces, or twisted string Hilbert spaces. Okay. But then again, by Dehn twists, you see this is not enough for modular invariance. You must also include GG, G to the n minus 1, G, right? You to get that. And this level matching condition that I'm talking about is the statement that when I do one more Dehn twist, right, then which goes to G to the n, that better be the same as the first one, because we are talking about an nth order. No? That gives a very non-trivial condition, which is called the level matching condition. So that condition is what I have written down here. Okay. Equation number 8 there. Yeah, that is the condition. And furthermore, I should also point out that there are some peculiarities for the asymmetric orbifold. In this diagram, you see, when I did the, this is by the way, it's called S transformation. When I go from here to here, there are some numbers which come, some numerical factors which come in the front, okay? That numerical factor happens to be something like this expression which I have written down here, which is square root of determinant prime of 1 minus g divided by the order of I star over I. Okay? Now, in order for this theory to have any Hilbert space interpretation, that number better be an integer, right? Otherwise, it would make no sense. Now, one can show that, in fact, it is generally, it's not a new condition. It is automatically satisfied if your original lattice was even and self-dual, if original gamma lattice was even and self-dual. So this is not a new condition, but I mean, it's not an extra condition. This is automatic. Furthermore, what is interesting is that if you look at the vertex operator algebra, okay, the vertex operators of the untwisted theory, no? the algebra of that, then the dimension of the irreducible representation is precisely given by that number, the square root factor. Okay. So which tells you that these twisted sectors, under the action of the vertex operators, they transform into another, and it's is a irreducible representation. It's an integer, yeah. This is an integer, yeah. Yeah. You see, that it was, in fact, that was initially the kind of, many people were not even looking at the asymmetric orbifold because they saw that there was a square root appearing. And there was no way to, I mean, how can it be? How can it make sense, no? But then it was shown by various mathematicians, Conway and Lepofsky and so on and so forth, that this is, I mean, they obtained some results, and if you apply that to the self-dual lattices, then it's automatically true. Sorry, repeat. You take the positive square root. Yeah, it's a positive square root. Yeah, right. Yeah. No, sorry. No, what did I do here? No, this I did already. Yeah, so the next one here. Okay. So this, the asymmetric orbifold details are all given in these two papers, 1988 and 91 papers. So what were the conclusions? By imposing level matching conditions and choosing different values of R, we were able to get all the Nikulin points in that original table that I showed in the second page, except for these 2 points. RA delta equal to 1, 1, 1 and 2, 2, 1. Because in these cases, I is very small. The dimension of I is very small. It's just 1-dimensional or 2-dimensional. And it didn't have, there was not enough space to put this shift vector V. This was coming from the level matching condition, right? This level matching condition, yeah, that equation number 8. That tells you that V was a shift that you have to put inside the in the invariant directions. And it depends on the S, or in other words, R. It depends on the R. For for S equal to 1 and 2, R equal to 1 and 2, V square is not equal to 0. So you have to put the V somewhere, okay? And there is simply not enough space to put that. No? So it's a matter of the lack of space there. But this could be remedied by, if you compactify on one more spectator circle, no? There's sufficient space to put these shift vectors. Only thing is that in 7 dimension, we cannot get those models. In 6 dimension, we can get those models. Now, this is the important point that I want to emphasize, that all the remaining points can be connected to each other by the mechanism I mentioned, going from Higgs branch to Coulomb branch from the field theory language. I first described that. But okay, so this is, yeah. So on the M theory side, these transitions will be non-perturbative, right? Because these are topologically distinct Nikulin spaces, right? So that's very difficult to study in the M theory side, but on the in the heterotic side, it's perturbatively realizable. No? Another point to mention is that most of the Nicolin points do not admit spin structures. Okay? So what does it mean? So remember, what is M theory? M theory is a theory of membranes, right? The low energy effective field theory of M theory in 11 dimension is the 11-dimensional supergravity theory, right? And then on top of it, we have membranes. No? That is the M theory. Not much has been understood because membrane theories are very, very difficult to quantize. So I don't think, I mean, that's still open issue here. So we cannot do much with the M theory at this stage. Only thing we know is the effective field theory is 11-dimensional supergravity, no? Plus membranes. So what this is saying is that, so you see that from the fact that there is no spin structure, that tells you that if I start from the 11-dimensional supergravity fields, the massless supergravity fields, and you do a Kaluza-Klein reduction on this Nicolin space, there will be no fermions, right? Because there are no fermions, spin structure is not there. So therefore, all the Kaluza-Klein modes will be bosons. Okay? On the other hand, in heterotic constructions that we are finding, there are fermions also. It's not just the bosons, but fermions also. But one can prove on the heterotic side that the fermions appear only for charged states. There are no neutral states, no neutral fermion states. So therefore, there is not a serious contradiction between the M theory, because what that says is that on the M theory side, fermions must come from the membranes wrapped on various 2 cycles of the K3, of this Nicolin space. That's not a serious, because membranes are localized. It doesn't see the full Nicolin space, the 4-dimensional space, right? Is some localized around some 2 cycle. So that can admit spin structure. But again, the details we cannot work out unless we make some progress on the M theory side, membrane theory, studying on membrane theory. Finally, one comment. I mean, all of this discussion, there's a little. It should be taken with a grain of salt, you know, because these theories these are not supersymmetric, so they all have tachyons. Okay, it is true that we can the large part of the moduli space, the tachyons are massive, so you can ignore them. Okay, in that case, all these discussions go through. Right? However, we have also seen in one of our previous papers that even though you may start from the region where there is a tachyon is positive mass, there is a quantum effective potential is generated, and it's no longer flat direction. There is a potential which drives you to the region where tachyons appear. So this is a kind of a question mark there. Okay. Yeah, I think that's all. I will just stop here. Right. Yeah. Yeah. Okay, I think the lunch time. Yeah.
So we'll meet at 2 o'clock after lunch. 2 o'clock.
Okay, good afternoon and welcome to the afternoon session. We are very happy to have Biswajit Chakravarti from Ramakrishna Mission, and he's going to tell us on the possibility of emergent curved momentum space geometry and its impact on deformed dispersion relation in Kappa-Minkowski spacetime.
Hello, I'm audible to everyone? Okay. So let me begin by thanking the organizers first of all for inviting me and giving me the privilege of speaking here in BalFest. I had also the privilege of attending the BalFest 80 in Dublin. So it is my really, I think I am very fortunate to see him again after 5 years, because we don't get to meet each other very often these days, and I think I'm meeting him after 4 long years. And this talk actually, my student Anisha, who is also one of the collaborators, who is here, gave a talk on this particular topic in 316 seminar of BAL a couple of months back, but it was bit in an incomplete stage. It is still incomplete, but we have made some progress based on some comments made by Bal and Kumar. Actually, TRG and Kumar has extensively worked on this area. So I think today I will try to convince them about these things before and get some feedback so that we can make some final changes and upload the paper in the archive and submit it for publication. So let me begin by wishing happy birthday to Bal. Probably it is advanced happy birthday. Your birthday, I think, falls on 22nd or something. 25, okay. Anyway, advance happy birthday to you. So, and this talk actually, let me give you a brief history before I go through the slides. It is almost for 10 years or 12 years that this idea of curved momentum space is floating in the literature, particularly group of people like Glickman and his other collaborators and Smolin, they are working on it. For some reason or the other, I was not very much aware of this kind of activity, particularly I did not take much of notice about its relationship with respect to Kappa-Minkowski space. Somehow it was my fault, I agree. But only recently, maybe 5-6 months back, I went through the paper, I found it absolutely fascinating. Some kind of possibility that can emerge in some regimes of quantum gravity, and it can have deep impact even for the kinematics and dynamics of a single relativistic particle, even if it is spinless, I found it very fascinating. So at the outset, I must tell you that the Kappa-Minkowski spacetime has different versions, so-called different avatars. And particularly the non-commutative parameter which are introduced, somebody take them to be real constants, as I will be doing here. Some people take it to be transforming like a Lorentz 4 vector and things like that. And then some people try to restore the symmetry by deforming the Poincare generators, by retaining the structure of the Poincare algebra intact. Some people deforms even the Poincare algebra, but all the time, of course, ensuring that when the non-commutative parameter goes to 0, then you recover your usual commutative structure. But the beauty of Kappa-Minkowski spacetime, or for that matter in generic Lie algebraic kind of non-commutative structure, is that the structure constant by themselves have the dimension of Planck length. So you can, in the unit of C equal to 1, it will be of the order of root over h bar times g. So if you come down to so-called, in the classical description, you demote the commutator to the level of brackets, call it Dirac brackets, in anticipation that it will be related to some form of constraint structure, constraint form of Lagrangian. So in that case, the effective non-commutative parameter will have the dimension, will have root over g by h bar structure, and it will have the dimension of mass inverse. So energy scale will automatically emerge even if you require that h bar going to 0 along with g going to 0, but the ratio is held fixed. So the theory automatically, the classical theory automatically get an access into a regime of quantum theory where you are automatically are having an energy scale. This gives rise to the possibility that you are going to end up with some kind of curved momentum space. In this kind of the scenario, that is reminiscent of what happened long back when Gauss discovered the Riemannian geometry. He first discovered the two-dimensional surface with negative curvature, and he found that there is no problem, it is completely consistent theory. And he said that if I can really demonstrate the nature obeys this kind of curvature, means displays this kind of curved surface, then automatically we are going to end up with natural length scale. So if he made a dictum, so to say, I am rephrasing it, the exact wordings I don't recall, that if it is possible to have a non-vanishing value of the deformation parameter having the dimension of length, then it should better have this non-vanishing value. There is almost 0 probability that is measured 0 actually, that it will be fine-tuned to the value exactly 0. So here also, the moment we have got some mass or energy scale, it is quite expected that the momentum space also will become automatically curved. And this is also reminiscent of what happens in usual special relativity, because the 3 velocity space, there actually is a curved space, because it is, as you can see, and the addition of velocities in, if they are non-collinear, they loses their commutativity, and if you consider the addition of 3 such velocities, it loses their associativity, giving rise to Thomas precision and all sorts of things. So these examples are, there are plenty of such examples are there in the literature. So here too one expects something like that. So the question is that how do you deal with this curved momentum space and what can be its impact? To understand clearly this impact, one has to, as I have seen in the literature, they emphasize that one needs to study actually the kinematics and dynamics of multi-particle system. Because if you consider collision of 2 particles and study the addition of momenta, 4 momenta, I just say momenta, and if you find there is a nonlinearity, you find that there is, they do not commute, then you infer that the manifold actually is not, means the manifold has a torsion, and if you lose associativity, then you have curvature, and some cases even the metricity condition may be lost. So it is not even a Riemannian manifold, it may be something which transcends that. So keeping all these things in mind, my aim here is something very modest. I'll try to find out, construct rather, a relativistic, Lagrangian of a relativistic particle, spinless relativistic particle, and try to see what kind of impact it can have, the curved momentum space have on the kinematics through the deformed dispersion relation. So I think that will be good enough for me for 35 minutes talk. So let me begin by flashing the slides one by one. So the classical theory of gravity, as I told you, is expected to be overtaken by some form of quantum gravity, which form we don't know. But one generally desires to have some robust feature which may survive any future theory of quantum gravity. And in this example, if I consider particularly where the h bar and g simultaneously goes to 0, but the ratio is held fixed, then automatically provides us with a mass scale. And this mass scale ideally should be determined through experiment. Otherwise, I can take it to be arbitrary, but roughly you can think it of the order of the Planck mass scale. And in the context of Kappa-Minkowski space, actually this mass scale is taken to be another invariant quantity, and Kappa-Minkowski space was introduced more than 20 years back by Emilio Camilina and all other people. And crowd momentum space, the relationship were also introduced. And particularly an interesting model in 2+1 dimensional gravity, actually when you recast in terms of Poincare gauge symmetry, which being a topological theory when coupled to relativistic particle, point particle, one can show the momentum space indeed becomes curved. Here the Newton's constant have the dimension of the reciprocal of the energy scale. So here you don't have to take any limit or things like that, but in 3+1 dimension you have to take the limit to come to that regime. So these are the some of the references. So my aim is to construct the Lagrangian free relativistic particle moving in Kappa-Minkowski space-time, look for deformations in dispersion relation, if any. As a good plausible source, crowd momentum space can occur here, as I have explained. And my plan of the talk is revisit. I'll start because, as I told you, the literature is huge. And we have seen many of the papers, they take different points of views, as I have already emphasized. So I'll give you some sample references. These are not exhaustive at all. In fact, the paper which we are going to upload very soon in the archive, we hopefully will insert more references. But here, as it stands, it is not exhaustive at all. So construction of relativistic particle Lagrangian Kappa-Minkowski space-time invariant under above mentioned symmetry, emergence of crowd momentum space and its impact on deformed dispersion relation. This problem of crowd momentum space, the metric, as you'll see, it involves a lot of intricacies in the sense that the kind of Kappa-Minkowski space-time I am going to introduce, it involves a scalar deformation parameter, in the sense that the relation 1, x mu x nu, commutator is, I have taken it in the more general form, I a mu x nu minus a nu x mu, or a mu set of 4 real numbers, strictly. So they are just constant, 4 constants. So the commutator with p mu as well as p alpha and m alpha beta vanishes, period. So they are just constant, they don't transform. Nevertheless, here also we can formally write a mu as eta mu nu a nu as a set of new scalars. Just a0 is up or down, doesn't matter, the same. ai down is minus of ai up. That's a set of 4 new scalars. Formally, I can still write here, so as if I am raising or lowering indices of 4 vectors. Also, I take the magnitude of a0 exceeds that of square root of the sum of the squares of other ai's. That's what is required in the subsequent analysis. And this a, I take it of the order of the Planck length. This algebra as it stands is not stable under Poincare transformation. And to retain the Poincare transformation, one needs to deform the transformation rule. And what we'll do here, we'll take the Lie algebra to be the usual Poincare algebra itself, where I do not touch the Poincare algebra at all. The generators by themselves will undergo deformations in order to preserve that. That will show at the fag end of my talk, albeit classically, but quantum mechanically is a bit difficult. Means up to some operator ordering, it will hold at the quantum level also, that I don't bother. And M mu news and P news are the respectively Lorentzian transformation generator. So strategy is the following. We demand that the 2 remains undeformed. Deformed infinitesimal ISO 1,3 transformations, ensuring covariance of space-time algebra. Covariance means the commutator algebra is stable under the transformation. Generators and corresponding coproducts are also deformed. These results are already existing in the literature. I'll just mention it for completeness. I'm not going to pursue any multi-particle analysis of any multi-particle system. So I'll just mention it in one of my slides. And so to proceed further, what we do, we consider the action of the Poincare generators on x mu's. And here the action, I take it to be deformed, and these deformation parameters are captured through these three objects, psi, phi, and chi. So here the parameter a's are occurring. So we require that whenever a tends to 0, these quantities will vanish. In the phi case, it will become 1, and psi and chi become 0 in the limit. So the deformation has to be chosen quite wisely in the sense that we should restore. So we are revisiting this problem. Again, the results are already existing, but they're scattered in the literature various ways. So we have tried to derive it in our own way using the template of this paper, mainly this reference one, Koch et al. They have done it for the Minkowski's case. So we have, it was a long calculation. I just made a quick revision of this thing, review of the work. So it is an old result, and order of the deformation parameter will try to maintain it at the linear level as possible, because the moment you go beyond linear linearity, it proliferates like anything uncontrollable, becomes uncontrollable, and we have to, at the end of the day, ensure the proper commutative limit is reproduced. So what we do, make use of the Jacobi identities, where capital G refers to the Poincare generators, M or P, translational Lorentz, homogeneous Lorentz generators. So Jacobi identities of two types, where X occurs only once, and the second one where X occurs twice. So you write down the detailed algebra, Jacobi identity, and then carry on this analysis, make certain and such. Admittedly, this and such were, means when we made this and such, symmetry arguments of course helped us, but prior knowledge of the structure was beneficial for us. It was ultimately we could recover all the results. The details are not required. Finally, what we find is that M mu nu x nu commutator is given like this. So you can see there is a term where in the 14, 15 there are terms which depends on mu's. So the moment mu goes to 0, you recover the commutative limit. So the important thing is to realize that the p mu x nu relation, there is a factor which multiplies eta mu nu, which is entirely momentum dependent. And this actually opens up the window for interpreting it as some sort of momentum space tetrad that we will see later. Okay. So the deformed transformation compatible with the space-time algebra is given like this. You can just apply this commutator and find that deformed transformation is given like this, and deformed Lorentz transformation is also given like this. And clearly the transformations of, they say x's do not transform like vectors anymore. And just I show you the deformed co-product, which are also, which are basically necessary if I want to discuss multi-particle systems, which I am not going to discuss here. So I skip through this thing, which are available in the literature. So now the task, our main task begins. What we want to do is we want to construct the Lagrangian of a free relativistic particle. So as I told you, we are not touching the structure of the Poincare algebra. So Casimir operator remains undeformed. So unchanged mass shell condition. So this is the advantage. If you touch the Poincare algebra, if the P mu algebra is not the usual one, then you are a bit difficult situation, because you don't know how to the Casimir, you don't know how the particle classification Ella Wagner will go through. So here you are sure that these things are not touched and they go through as usual. So we want to look for any deformation in the one particle system that I have already mentioned. So we will try to construct a relativistic one particle model at the classical level. The dynamical model should be such that the action of the Lagrangian should respect the Poincare symmetry. Not only that, even the commutator algebra should also respect the symmetry. This apparently has not been done. Glickman has constructed an action for a relativistic particle, but at the end of the day, only the action part respects the Poincare symmetry, not the algebra part. So stability of the algebra is not ensured. So here, as I told you, we come down to the classical level. So what we do, we demote the commutator to the Dirac bracket, dividing by IH bar and taking H bar going to 0 limit, and introduce this new A mu, which is A mu divided by H bar in the limit H bar and G both going to 0. So, this furnishes us with a mass scale in the unit C equal to 1. So, these are the Dirac brackets. I am calling it Dirac brackets in anticipation that we are going to identify them as the Dirac bracket of a first order constraint system. So, the thing is that usually if you are given Lagrangian, you know to run through the Dirac algorithm, end up with the Dirac brackets. But here the task is opposite. So, this makes it a bit non-trivial. We have the Dirac bracket. So, from there we can identify what is actually the inverse of the constraint matrix, not the constraint matrix. Then from there the constraint matrix, and from there we have to identify the constraint, and from there we can guess, and after that we can check whether the first order Lagrangian is really yields that kind of Dirac bracket or not. So, this is our answer. We write the first order Lagrangian where x and p are the configuration space variable in extended phase configuration space. So, pi, there is a pi's for x and pi's for p. So, these are extended phase space now. They satisfy usual Poisson bracket equation 25, and the structure of the constants now, since the first order is usual given in 26. So, this helps us in now if I just relabel the x mu's and p mu's as xi mu 1 and xi mu 2 and recall the definition of the Dirac bracket, you can see that you can obtain the inverse of the constraint matrix as given in 28, and from there again obtain the constraint matrix lambda as given here, where T and C are defined below, equation 29. So, from there we have the constraint matrix, and we can, after some guesswork and some hit and trial method, we arrive at the following structure of F mu and G mu, and ultimately the Lagrangian 32. So, this is the first order Lagrangian. We have verified it through running backward again, or backward means from this Lagrangian we carried out the constraint analysis. We could reproduce the usual Dirac bracket that we started with. So, things are completely consistent. The thing that I have changed here is equation 32. In the last talk that Annesha gave, Bal was unhappy why we changed this first class constraint from p square minus small m square to f of p square minus capital M square. So, the answer lies in the argument which is given in the literature already by Glickman, Smolin and all, is that usually when you deal with the flat momentum space, the Casimir p square is regarded as the distance in the momentum space from a distinguished point which is taken to be p mu equal to 0 to some given p mu, and carry out the computation of the straight line distance from the origin to that point p mu. That will give you the distance, and you can identify that as the Casimir. But the moment you say that the momentum space is becoming curved, which I will show now, that you can interpret that way, then you have to replace it appropriately by the geodesic distance coming from the origin to that point P. And the geodesic in general will not be a straight line anymore. Okay. So, you can write down the Lagrangian in this way. So, E tau is something like a Lagrange multiplier which enforces this modified mass shell condition. This I am of course writing in anticipation, and p square equal to small m square is the eigenvalue of the Casimir, that original one that I had chosen. So, my idea is to argue that the small m will be some sort of a quote unquote the bare mass, and capital M will be the renormalized observed in the spirit of quantum field theory. So, you see now the Lagrangian I can write down, I can see that if you compare with these flat space Lagrangian, one form so to say, which I have written equation below 33, where you have delta alpha with the Kronecker delta occurring, but here you now have what is shown in here in the blue form, blue color is EP B mu, which is actually this phi inverse P times delta beta mu plus this quantity, whatever is the blue. So you have to have this object inserted here to obtain the first order Lagrangian. And the origin of it stems from the, as I told you, in the original, rather the inverse of it, occurs in the XP bracket, which is the E inverse P B mu. In the bottom, you can see this relation occurs there. Okay? So this helps us to construct a metric out. So I interpret it as some sort of a tetrad and construct a metric out of the tetrad in momentum space, and I call it G mu nu tilde eta AB E inverse P A mu E inverse P B mu. Upon simplification, it takes this form. This form is quite nice. It is symmetric under mu nu, everything very nice. But the problem is that forget about diffeomorphism, covariance under diffeomorphism. It is not even covariant under Lorentz transformations, because as I declared at the outset, these A mu's are actually scalars. So the way out is that to make sense out of it, the only way we found is that we say that we take these P mu's to be some, means you have, so all these P mu's are related by Lorentz transformations. So they are referred to some inertial frames you can think of. You choose one of the inertial frame as some reference fiducial frame. And once you have chosen this fiducial frame, subsequent transformations, if any, be it Lorentz transformation more general or more generally any diffeomorphism transformation, require the G mu nu will transform just like a covariant second rank symmetric tensor, as I have shown here in 36. The advantage of these, the d square, the line element, remains invariant under such an arbitrary diffeomorphism in the phase space, in the momentum space, momentum space script P. So this ultimately I have to show that is independent of the choice of the fiducial frame, and that will turn out to be satisfied. So let us take this approach, and then I mentioned one interesting thing is that the P mu's they are transforming as vectors under Lorentz transformations, but they don't transform anymore under diffeomorphism transformations. Rather, dP mu's, they transform as 4 vectors under this thing. Nevertheless, as it turns out, G mu nu, P nu can be simplified further and given in terms of these things, equation 37. So it becomes, since P square is equal to M square, it turns out to be just a number, and it remains invariant under diffeomorphism also. And it becomes possible because you don't have any term like A dot P. If there are any term of the form A dot P, this would have spoiled its symmetry completely. This is fortuitous for us. So now we calculate the geodesic distance, and geodesic distance is given like this. From the origin, this is a distinguished point to the point P, we have to calculate the distance, and we shall identify the mass shell condition now, modified square of the geodesic distance to the capital M square. And computing the geodesic distance is a very non-trivial job. So what we make use of this differential equation said by the geodesic distance, del mu dp G mu nu P del nu dp. This del mu, their differentiation with respect to in the momentum space, del mu P rather I should write anyway. And this is a well-known differential equation, geodesic equation is satisfied. And now we require this C, that means d square also should be function of P square. This I require because it should also commute with all the Poincare generators. So it should be function of P square. And with this and such, I can really substitute it and obtain 39, and subsequently I can solve it, and after solving it I will get a very nice result. Is a M square is given by this 1 by a sine hyperbolic inverse A times root over P square whole square. So where P square is M square as usual. In A I just written a shorthand of mod A that I introduced earlier. So this gives a relation between capital M and small m. So identify M as a renormalized observed mass in the contrast to the bare mass M. And you can see the diagram is something like this. If you plot the diagram, So what becomes, initially they are almost at 45-degree tangent, but as as determined by the scale of mod A, this becomes insensitive after some time. It starts getting, there is no upper bound as such, but the tangent becomes flatter and flatter, so it becomes insensitive to the growth of small m, and this is the feature we observe. And to cast it in the form of usual, because as we said that our space time remains flat, it is the momentum space which gets curved. 10 minutes, okay, I will finish it here. Momentum space which gets curved. So what you can do, we can make use of what are called Riemann normal coordinates as defined, introduced at the tangent plane at the origin of p mu equal to 0, and can rewrite this distance square in terms of the normal coordinates. I introduce pi 0 square minus pi vector square is equal to capital M square, and write a relation between pi a and pa. This pa's are the same as the original p mu's actually. I have changed the notation in between when I introduce a tetrad to indicate local Lorentz index and another one for the world index, so to say. And pa by m is nothing but the unit time-like vector, so they can be parameterized as below, as I have shown in the bottom of the slide, unit time-like vector. So you can see that once you cast it in the form of pi 0 square minus pi vector square, this is exactly of the form of what you expect, because this is with respect to the flat metric. Because once you use the Riemann normal coordinate at the origin, the metric becomes flat at the origin, so to say. And everything is described in terms of the tangent plane coordinates. And then it takes precisely of this form. So our claim is that the pi mu's are actually observed for momentum now, and capital M is the observed mass, renormalized mass. I want to use this terminology particularly here in the spirit of quantum field theory. So finally, I just want to pass a remark that I can introduce some sort of coordinate carrying out some non-canonical transformation using this tetrad again, go to this, introduce the Q's which are commuting. You can see 45. And using that, I can use the deformed Lorentz generators, and these expressions are all the classical level. And you can see that the classical level itself, there is a deformation. So Lorentz generators are indeed deformed. Capital P undergoes no transformation, undergoes small p as is shown in equation 44. So the generators are indeed deformed, as can be seen in the classical level itself. So finally, I conclude. We started by revisiting deformed Poincare symmetry compatible with Kappa deformed algebra in algebraic approach. We also constructed dynamical model for relativistic free particle invariant under deformed symmetries. From these, we could interpret a manifestation of non-trivial momentum space geometry yielding a deformed dispersion relation. The momentum space P in our case cannot be identified as a group manifold. This is a departure from the Glickman side. They identified their momentum space as some sort of a group manifold, part of the de Sitter space, which they call it AN3. But we are not getting anything like that. So the advantage of getting a group manifold is the composition of multiparticle momentum becomes, can be rid of basically from the group multiplication rule, which we cannot do in our case. So all that we have to do is that we have to write down similar multiparticle Lagrangian and then see what is the symmetry and find the generator and study their composition rule. This is the work that we intend to do in future. So it will be non-trivial job, of course. So it becomes a bit difficult to compose individual momentum of multiparticle system to obtain the total momentum. It is therefore quite interesting to see how one can construct a multiparticle action in presence of interactions taken to be simple collisions and study the corresponding Hopf algebra symmetry. So in fact, recently, just last month, this Glickman and Arjano has come up with a paper where they have got good, very well written paper actually, and they actually discussed about the loss. Title of the paper I have forgotten exactly, but the last line says that it is identity crisis, just like the kind of thing that we discussed in the Moyle plane context. So it is more severe there in the Kappa-Minkowski spacetime. So we'd like to look at those aspects more carefully in the future. With this, I thank Bal again.
Thank you, Biswajit. Are there any questions?
Yeah, Kumar, I expected.
First of all, why did you construct the Lagrangian? You don't seem to have used it.
Can you repeat the question in the microphone?
You constructed the Lagrangian, right?
Yeah.
But did you use it anywhere in your analysis?
Yeah. From the Lagrangian itself, I could read off the symmetry generators. I could verify this Lagrangian, enjoy the same symmetry of the Poincare symmetry, and as well as the commutator algebra. The total symmetry is dictated by the symmetry is given by the Poincare generators. Right. So study the symmetry aspects, I need to study the action and the Lagrangian.
Okay, and the second question is this last reference that you showed, Arzano and Kowalski. Yeah. They had some statements about the spin statistics, right?
Yeah.
So do you have any comment about that in your analysis?
Frankly speaking, I am yet to read this paper carefully. I just glanced through it very recently, last week. I want to pursue it more carefully in the next few days.
Okay, thank you.
So maybe this is a simple question, but in the initial deformation you wrote in Kappa-Minkowski, could I have not taken the A vector to be null? Like it would still be non-trivial?
That we cannot take. In our analysis, we cannot take. We cannot reach that kind of conclusion. At some point, I have to take it to be, people consider all kind of things. Even I think my Federle Lizzi will be talking about Kappa-Minkowski or some variants of it just immediately after me. He will be talking of all sorts of possibilities. But to get hold of this kind of dispersion relation, I have to take it quote-unquote time-like. Just as if they are vectors.
If you just started with the same deformation, x hat mu, a mu and all that, I could have taken A to be null and still non-trivial deformation, right?
Yeah.
Only the mass is not now renormalized, it will be the same mass. But you still have one curved metric, no? Even if A was null?
I don't know. We have not looked into this thing. At certain stage of our calculation, I found that we have to impose this condition. And if we do not impose this condition, it is not clear. We have not investigated it.
Your while being your tetrad, right? Capital A, E, which is function of P.
Yeah, there are two A's, one for the classical deformation parameter, another is quantum deformation. When I demote from the quantum commutator to the Dirac bracket, so to say, I have to divide by IH bar and take the limit H bar going to 0.
No, I was just saying that the metric.
Metric, okay.
The tetrad E as a function of P, right?
Yeah.
I thought that would be non-trivial even if A was null. I mean, the form of that.
I cannot say offhand. Maybe you are true. I'll check it and let you know.
One small question. The manifold or the momentum space, you said it is not a group manifold.
Yeah.
Is there a way in which you can understand something like a quotient space or coadjoint orbit or any of these things?
Not really.
Because still group theory will be useful.
Yeah, it will be nice to see whether this possibility is there, but I doubt whether this kind of possibility is there here or not. This is a problem actually.
There is no. There is no information about the manifold structure of.
Nothing that I can say beyond this, based on what I have already told at this stage.
Can you find out what are the light cones and what happens to causality?
I have not looked into it, but yeah.
Otherwise, or how do I write the equation for electromagnetism?
Yeah, this is electromagnetic. I have to consider field theory in this kind of space.
But light cones you can do.
Yeah, light cone I can do.
That will give at least how the lights can possibly propagate.
Yeah.
And so one can ask about causality, and is it something screwed up or is it decent? Because it looks like mixes position and momenta.
You see, our analysis is restricted to massive particle first of all. So what happens to a photon is a bit difficult. The background metric that we see is, we are claiming the flat, it is actually perceived by so-called zero Ford momentum in the limit of p mu going to 0, where g mu nu goes to eta mu nu. But exactly what happens in the case of a photon, that we have to see.
But you can ask what is G mu nu?
Hey, dp mu is equal to 0.
Is zero. That will give you the
Means
light
one expression we had, but for the massive case, I can show you that this expression, equation 37, for example, but it is for p mu, but we have to calculate analogously gp mu, dp nu, and set it equal to 0. That's what you are asking, right?
And you can look at the boundary, and that will give you the light cone.
Okay.
If it is this codes for all mass is an open set, so there is a boundary, and you can take the boundary. You know what the light codes are.
Okay.
Zero, yeah.
Yeah, that may be done. Yeah, good.
Hello? Yeah, Professor Lizzie has a question. You can unmute and ask.
My question was exactly the same one that was asked before. What happens if it's null like the vector? And Vishwajit already answered. By a coincidence, I wanted to ask the same question as someone else. So
I could not follow.
Saying that he had the same question in mind that Bal asked, so he's okay.
Okay.
He has no more questions.
Okay.
Yeah, we can hear you, sir.
So if there are no further questions,
Question, can I ask?
why not?
Okay. See, this is a general question, as has been emphasized by Bal and many other people. So classical physics is a probability theory on a commutative algebra, and quantum physics is a probability theory on a non-commutative algebra. So, but here you have both H bar and non-commutativity at the same time. So can you really distinguish the two?
No, here you see the first case when I started the quantum level, I distinguished between these two non-commutative parameters. Two different A's I used, you remember. One is the curly A, so to say, another is another type A. So in one case, it has got length dimension. Typically, you take it to the order of h bar g. And the second case, when I divide by I h bar and take limit h bar going to 0, then the Planck length actually disappears. Okay, but I simultaneously, so what we will get is something like root over g by h bar. To make it survive, I have to simultaneously demand that the g also goes to 0. Holding the ratio fixed, and this furnishes us with the mass scale, so non-commutativity will be related to the inverse of the mass scale there rather than the length scale.
Now see, my question is a little bit more general. I'm saying if I just look at the algebra of observables, and I find it's a non-commutative algebra, can I say whether it is quantum theory or it is a non-commutative geometry? Can I distinguish?
I think you can do it, but the deformation parameter will be just changed. Nothing much will change. No, Sachin, what do you think? Means of course, classically, if you multiply, since only Dirac brackets you are deforming, if you multiply the observables, they will be commuting. they will have commuting sister algebra maybe.
Okay, thank you.
So on this very interesting point, we will unfortunately have to stop, but we will like to thank Biswajit one more time. And the next talk is on Zoom by Fedele Lizzi. He's going to tell us about quantum space-time, non-commutative geometry, and observers.
screen and I will, how do I, no, I need to go here, new, enter full screen. Okay, can you got it? Okay, I trust you can hear me, otherwise somebody would tell me something. And,
yeah, we can hear you.
Okay, that's the title of my talk, and I will talk about things in with collaboration with several people in not all together in the same paper, but in the various combinations. And my affiliations is, of course, the official one, and that there is the affiliation which I will bring with me always, which is room 316 in the physics building. And okay. So everyone starts with thanking the organizers, and of course I thank the organizers. I'm very sorry I'm not able to be there in person, and but I had another acknowledgement, which is actually taken from 1985 in my doctoral thesis. I was looking at it for some reason some time ago, and I found this acknowledgement. And I read it because after 5 years in Syracuse, there are many people I would like to thank. And the first one is Balachandran, Professor A.P. Balachandran. And he taught me the most of what I know and reproached me for not studying most of what I don't know and I should know. And he showed me how to work and gave me the honor to be one of his collaborators and friends. Thanks, Bal. Now, this was written in 85, and in 26, I will retire, and if I were to write a retirement thesis, it would be the same acknowledgement with the same, I wouldn't change a single word. So of course, unfortunately, I would have to change the 5 in 46, and I would change Syracuse in Oxford, Trieste, Naples, and Barcelona, but the first and foremost I would keep. So I think it's fitting to start this with this. For some reason, the arrows don't work, and I will have to go with the mouse. Okay, so now I'll start with a preamble, which is probably pleonastic in this audience. Gravity is the theory of curved space-time, and in order to quantize, I can quantize G mu nu, but this doesn't work very well. Nothing works very well. And the idea behind non-commutative geometry, and is quite fitting that this talk comes after the one of Bijwait, is somewhat complementary to it, and it overlaps a lot with the talk I gave in Kolkata. It looks like yesterday, but there was the pandemic in between. I think it was 4 or 5 years ago. And it's just, I will repeat part of the talk and then go ahead. And so we need some quantum space-time, and there are several people in the audience and several people that talk who have been working on this quantization of space-time. Okay, one way to quantize space-time is to take coordinates which do not commute, and Doppler, Fredenhagen, Roberts have been working in this case, the somehow simplest one. This is a replica of of quantum mechanics, just change h bar with theta and make this, and the x with x and p and make this. But this doesn't have Lorentz invariance and maintains translation invariance. Of course, this is not a problem in quantum mechanics because we have a symmetry which rotates, we don't have a symmetry which rotates coordinates into momenta. So I'm going fast on this because several people have been giving similar talks, but the importance of symmetries is quite important. And one way to do is to work with some concomitant space, a quantum space, which has a quantum symmetry. And now in partial answer to, I think it was Kumar, question, I call quantum something which is described by non-commutativity. So quantum for me might be also when h bar is 0. And ideally, and I've written recently a paper, you can have cases in which the non-commutative of space and non-commutative of space-time are present. But for this talk, when I call quantum, it's anything which has non-commutativity in it. So it's a matter of, it's a definition. Okay, so we need quantum symmetries, and I'm going fast on this because I want to be go slower on novelties. So one way is to have a kappa Minkowski. A kappa Minkowski comes as the homogeneous space of kappa Poincaré, which is a deformation of the Poincaré group, which actually was done before kappa Minkowski. And kappa Minkowski is described by this non-commutativity. Later on, I will, okay, this is the time-like kappa Minkowski, the one that also Bijwait was describing. There are other versions, like the null version. I worked on this with Fabio Mercati, but I will not discuss it. And later on, I will have a variation of this theme, which we call Rho Minkowski. And I will describe this later on. Now, as I said, for me, a quantum space is a space in which coordinates don't commute. And I will use the usual techniques of quantum mechanics. And I will remind you, I'm sure you know it. If you don't know it, you, of course, are not able to follow this seminar, but I want to give you a perspective on a quantum space. So starting with the most famous quantum space, which is quantum space of a particle, quantum particle. So I start with a classical 6-dimensional space-times, which is described by these 6 coordinates, or 3 times n if I different number of coordinates or more particles. But the important bit is this non-commutation relation. And I represent this, of course, as operators. And usually I represent them as operators on L2 or R3. Now, I start with a 6-dimensional space and I have a smaller number of, this is 6 and this is 3. But I need these 3s because I have a complete set of observables, which are 3. And usually this is the formation, the representation that I use. Q is a multiplicative operator, and P is the is a derivative, and the scale appears here. Okay, Q and P are self-adjoint unbounded operators, and the spectrum of them is the real line for each of the I. And they don't have eigenvectors, they have improper eigenfunctions, they are distributions. We know how to deal with them. Since the QI commute, it's possible to have simultaneous improper eigenfunctions of them, and they are the delta Dirac, delta distribution, delta functions. So for a particular vector, and this is a point in R3, and but then if I want to look at momentum, for a particular momentum P, I have plane waves. And I have this formal eigenvalue equation. How do I find this? Well, I have this formal eigenvalue equation, and there is an H bar here, which I am will go into the alpha. So this is the formal eigenvalue equation, and I know that there is no solution of this, but I know that there are distributions, and if I require P to be self-adjoint, and the domain of the function to be absolutely continuous function, so I enlarge also a little bit, this is the domain of self-adjointness. I know that alpha must be pure imaginary, because the distribution must be well-defined on the well behaved at the limits in plus and minus infinity. So you know this, and there is an H bar here missing, and so this you have learned several years ago. Now, improper eigenfunctions are infinite plane waves of a particular frequency, and since plane waves are not vectors of the Hilbert space, there is no quantum states which would give us a measure exactly the values H bar okay. Nevertheless, we know how to deal with this. We do wave packets and everything. Now, what I've done here by writing e to the I q, the plane waves, and I've chosen the qi, the 3qi, as a complete set of observables. That's why I'm representing on L2 over 3, and because I need 3 quantum number. And of course, the psi of q is the density probability of the particles. Psi is complex and contains information about the density probability of momentum operator. This is another important thing. You cannot do quantum mechanics with real wave functions. Wigner, Beppe Marmo would talk about this for a long time, but that's the way it is. There are profound reasons for this. Of course, you know that we could have chosen P as a complete set of observables, and if we choose P as a complete set of observable, then I do a Fourier transform. So I basically Fourier transform the functions from functions of P to functions of Q to functions of P, and everything is dual in this case because the Fourier transform is somehow symmetric. Transform and transform are very symmetric. There is a sign with changes in the nucleus. But I could choose other complete sets, for example, the number operator, angular moment, the 3 number operators, or I can choose the Hamiltonian of the harmonic oscillator, LZ, and the square of angular momentum, everything. So all this we know fairly well. No one understands it, as Feynman said, but we know. Now, if I have a different observer, he will have his own Hilbert space, and they will have his own set of observable and so on. So if I have observers, I have a tensor product. Now, this is not a problem, of course. No one thinks much about this thing, because we can have unitary transformations, very simple, from one set observer to another one. But I remind you that there is a coproduct in this way. So I have to put together representations. Now, quantum groups have taught us that there is more than just the Lie algebra structure. A symmetry is really a Hopf algebra. So I have to put together representation. And usually this is done in a co-commutative way. So I put representation in a let me say, trivial way. And we don't even notice it. But in a deformation of the algebra, if the Lie algebra is deformed, also the group is deformed. Also the way I put together transformation is deformed. And Bishwait was showing cases of this kind. So let me briefly say what a Hopf algebra has in addition to a Lie algebra. So it's an algebra, it's a set which has 2 operators, sum and Lie bracket in this case, and the set of functions is another example of an algebra in which in this case is multiplication, it's not the Lie bracket. And the functions are associative. The Lie algebra is not associative, but it has Jacobi identity. Now, while a product is a map from 2 elements of the algebra into a single element, the coproduct tells how to put together representation. Formally, it is a map from 1 copy of the algebra into the tensor product. So this is the fairly trivial and common example, and that's how I put together 2 representations. And this is basically the Leibniz rule. So if the Lie algebra I represent as differential operators of the first order, this is how I act on products. This instead is another coproduct of the co-commutative way, the simple ones. And this is what happens if I make multiplication of functions, because if I have functions on a group, this is the way in which I multiply the functions on the group, pointwise multiplication. There are 2 more structures, co-unit and antipode, which are dual to unity and the inverse. And they are important, but they are not relevant for this seminar, so I will not remind or describe them. Okay, earlier we discussed, there is a D missing here, quantum phase space, where the deformation parameter was h bar. And now I want to reproduce this discussion for Kaplan-Minkowski. Okay, now our four-dimensional space has different commutations. It's a four-dimensional, as I said, and the deformation parameter is lambda, which is, I call lambda 1 over kappa thing. And for when people did Kaplan-Minkowski, they were thinking of speed of light. So the classical case was recovered in the limit of the parameter going to infinity. I'm more in the quantum camp. And so I like to have classical limits when the parameter goes to 0. So this is a quantum space in the way I said before, and I will consider its kinematics and leave H bar alone for the moment. For this talk, I said I tried to do work also in a paper called double quantization. But this is a relativistic space, so I need to worry about Poincaré transformations. And I will do it in a moment. So I have the representation of the commutation relations, and I want to look at a representation of these non-commuting variables, so there will be operators, on a space. So although the space is four-dimensional, I will have to look here on the Hilbert space of square integral functions on a smaller space. Phase space, I do the same. And the dimension of the space is given by the set of commuting observables. And the set of commuting observables are the xi. So I take this xi to be multiplicative operators, and in this case, time x0 is a dilation operator. It's a dilation operator, then I have to add 3 halves because those two don't commute, and if I don't put 3 halves, this will not be self-adjoint and not even Hermitian. And there is an important thing to notice. I think that this has been noticed not very much by the Kaplan-Minkowski community. The Kaplan-Minkowski is really natural in radial coordinates. So this is the radial coordinates. And in fact, I'm sorry, the best way, in my opinion, to write the Kaplan-Minkowski non-commutation rules is the following. Is x0 commutes with every function on theta phi. Of course, theta and phi are not good variables. They are not self-adjoint. I'll discuss this later on. But the only non-trivial commutation is this one, is x0 r equals I lambda r. So, of course, we didn't discover this, but not many people have noticed it, have used it. And this gives us only Heisenberg uncertainty relation, this one. So there is an uncertainty between x0 and r. I have now reduced the problem to a one-dimensional problem, but it's very important. R is not is one-dimensional, but the measure in integration shouldn't be integral in dr, should be integral in r squared dr. So what's the spectrum of this operator? And I have to do the same thing that I did before, but now, to make a long story short, this is dilations, apart from the 3 halves. Actually, the 3 halves is important. So the monomials are the not the exponentials of imaginary quantities. The monomials with an imaginary exponent are the eigenfunction, improper eigenfunctions, and in fact those are the distributions, the improper distributions. Notice that there is r to the I tau, but then there is a r to the minus 3 halves. This is coming from here. This is very important because when I integrate, I think I said it later, no, I don't say it. If I integrate this monomial, I have to put an r squared in the measure. Therefore, this becomes r to the 1/2. Now, r to the 1/2 diverges on both ends of the spectrum, diverges in 0 and infinity, but diverges just about. It's the same that happens with plane waves. Plane waves at plus and minus infinity the integral diverges because it doesn't go to zero either way, but it just about. So it doesn't diverge brutally. So this is the same thing. In fact, is the key to these Mellin transformations. Quantum phase space were connected by a Fourier transform, and Kappa-Minkowski, I can have two sets of observables. R, theta, and phi. It's an abuse calling R, theta, and phi. So R and then functions and theta and phi. But I have another set of commuting observables, which is tau, theta, and phi. And I can have some functions, which are functions of R, theta, and phi. But dually, I can have functions which are functions of tau, theta, and phi. And the two of them are connected by a Mellin transformations in 3 dimensions. The measure is important. The Mellin transformation would have integral in the R, but here there are measures coming everywhere. And I can interpret this psi modulus squared and tilde psi modulus squared as the probability density to find the particle in the position R or tau, respectively. So now it's good to have an idea of the dimensional quantities which are involved. If I call t the eigenvalue of the time operator, this is x0 divided by c, the speed of light, then tau is tc divided by lambda. So d divided by lambda is a dimensional quantity. And this dimensional quantity is the dimension of a frequency, of the inverse of a time. And if I choose for lambda the Planck length, then this is 10 to the 43 hertz. So if t equals 1, then this tau, so t is 1 in a second, then tau is 2 times 10 to the 43, which is an extremely large number. But if t, say the time, is of the order of the Planck time, then tau will be 1. So keep this in mind. This tau is a small, the eigenvalue is a small number only if time is Planckian. Now I can try, I have to localize states. So in usual quantum mechanics, I localize states in a Gaussian. Here Mellin transforms and something, and I have choose to localize a state in this conical section. This is just because the calculations become easier. There is nothing mysterious in this. So I take this this localization in a section which has an angle of which is of the order of 2a divided by lambda, and a is the thickness of this. And if I take the limit of a going to 0, so the thickness going to 0, and automatically the angle closes, and then I have a localization in a point around the z-axis. I choose the z-axis just for. So this is the formula, but the picture is more. So I'm trying to localize this state in space at a distance z0 from the origin. And what happens if I try to localize in space to the localization in time? And the localization in time, this quantity goes to a constant when a goes to 0. And if the psi dagger squared goes to a constant, the localizing in time means delocalizing in space. In fact, I can see this by doing it's not simple to see from this. It looks like it goes to 0, but I have to make a series expansion of this for a around 0 and z0 around infinity, because I want to be distant from the origin. And I see the same thing, that the two Taylor expansions are the same, a and z0, a and 1 divided by z0 go together. So what does this mean? That if I sharply localize a particle far away from the origin, it means that the particle cannot be localized in time. And this is the uncertainty of Kappa-Minkowski that I described, which was here. Okay, so if I try to, I cannot localize both of them at the same time. I can only if R is small. Okay. As I said, only if R is small. I can localize at the origin. And the origin becomes an exceptional point, it becomes a point in which I can localize states. Now can do the same with log Gaussians and find the same thing. I will skip this. Okay, because of time, I will skip this, but I can localize now with the Gaussians, and the dual one are, of the log Gaussians in space are Gaussians in time, and so there is this localization. Let me go, I realize I'm going, because I want to do the variations as well. Okay, this is, I can do the double limiting, which are 0. Okay, this is, okay, sorry. I'm doing shortcuts, but I don't know if I'm missing something important. Okay, localization is at the origin at time t equals 0, but I can also localize at an arbitrary time, and this I can multiply the original state by this phase. This is a phase r to the it 0, and I call these states O tau, which means that I localize at some along the origin at some time. So now let me tackle this problem. I organized the origin as special point. So there is a point in the universe which is the origin, the place where the Kappa god, let me add another god to the pantheon, Indian pantheon. No, there isn't a special point in Kappa-Minkowski. That's what I argue. When I talk of the states, I assume the existence of an observer measuring the localization of states. This observer is located at origin, and for him, here and now makes sense. She cannot localize. I have decided to be gender fluid because I hate the stars and things like that. So I gender fluid. The observer changes gender throughout the experiment. So the observer cannot localize with precision states away from him as a consequence of the non-commutativity of Kappa-Minkowski. So this is the point. So I can localize where I am, my states are. What about other observer? And now this is a very good example because I'm doing a remote talk. In order to have a different observer, I have to translate Eigenboost. Usually these are done with an element of the group, the Poincaré group, but now I have Kappa Poincaré. Now, what in Kappa Poincaré, there is a tensor product because X going to X prime as the lambda, as I have to combine a transformation in the Poincaré group plus a mu. But now this lambda and this A don't commute. And in a particular basis, this is their commutation relation. Notice as Bijouet was commenting already, the lambdas are still commutative, but the commutator between the A's and the rotations of the A's or Lorentz transformation of the A's, but now the translations are not commuting. And what happens is an algebra observer, but I've chosen an observer, it's an algebra operators, but I've chosen an observer. The observer himself is a quantum object. And therefore, I will be described by some functions, but the functions of this A mu don't commute, and they have the same non-commutation relations as the x's. Therefore, in translating, I have an uncertainty in the translation. I have a very good example of this. Here I have a pen in my hand, so you don't know exactly where I am. You know that I'm in Naples, that I'm in Italy, and you have a fair idea, if you know geography, of where I am now that I'm talking. And well, I've been to Calcutta, but let's say that I have a fairly good idea of where you are, where Sachin is. And I've seen Sachin recently near a podium. Now, you know that I am near this pen. And therefore, you know that I can localize this pen very well. And I know that Sachin is near that podium. So I know that Sachin can localize this podium well. But you cannot localize this pen just because you don't know where I am. So this pen is not is not very well localized with you in Kappa-Minkowski space because it's far away from you, but you have no problems in knowing that it's near me. Now, we are in a classical world. So if I send you the GPS coordinates, you can localize me and the pen exactly. Also, the fact that it's slightly farther from my nose, if I send you a very precise coordinates. In quantum space-time, I cannot do this. And this is in words what I said in what I say here. And there are various aspects which can be described. But the important thing is that the observer is a quantum object. Quantum observers, in fact, subsequent papers that I've written, quantum observer in the title. I think this is an important thing. If one is doing quantum gravity, the observer has to become a quantum object. And this means that I cannot sharply localize observers. They will be described by functions, and I can explore this space observer, which is, again, states on an algebra. So I can define the identity transformation. So two observers which are nearby, and they are related by the co-unit. Fortunately, in Kappa-Minkowski, this co-unit is trivial, and therefore is in this representation of Kappa-Minkowski, which I'm using, two observers nearby will agree. This is not totally trivial. In Moyal case, this can be actually different if the two observers are rotated. Another thing is that since Lorentz transformations are commuting, we agree in directions. So rotations are not a problem. So the directions up of this pen, everybody would agree. It's the localization along R. So coincident observers are well defined. And I can, in order to change observer, a change of observer transforms the x's. And the x's and x prime correspond to different observers. This one is actually, there is implicit a tensor product times the one time is the identity times x prime equals to this. And therefore I have the same, I have to transform using the coproduct, which is non-trivial. And I cannot sharply localize position. I can not localize observers. That's what the change of the symmetry is telling us. But as I said before, since Lorentz transformation commute, I have no problem there. Okay, I can have the action of, I'm running out of time, action of the, see how in 1 + 1 dimension I can actually, which is simpler, I can actually have a representation of this, all these objects with a relatively simple non-commutation relation. The Lorentz transformation are given just by rapidity. There are only boosts. And I can actually find the representation of the translations and time translation and space translation, and they have this formula. And I can use, and I can actually verify how things go. states will be objects of this kind. We'll have tensor product. I could have entangled states. We haven't studied them in detail, but they will be something which in the observer space and something in the configuration space, and I can translate things. Now, the expectation value of the transformed coordinates is completely defined by translations. Translations are simple because two different observers are comparing position and not directions. As I say, the directions don't create any problem. I can have expectation values of objects, and here there is, I want to just stress the fact that...
Fidele, you have 5 minutes.
Yes, in fact, that's why I'm running. I'm running fast. All the uncertainty are, when I transform, I increase uncertainty. So if I have a chain of transformation, the state sort of gets degraded in the knowledge. Okay, this is, I said in words, this is ideologically, say, compatible with the relative localization, is Kowalski, Amelino, Friedel, and Smolin, but the context is different. So we don't consider momentum space, or we don't have curved momentum space. It would be interesting to understand better. Okay, I will now very quickly describe in 4 minutes a variation, because this is really a novelty with respect to talks I have already given. Let me discuss this Rho-Minkowski. Rho-Minkowski is a variation of Kappa-Minkowski. You can see that the algebra is time with x1 gives x2. So this is a rotation. This is a commutative space, and this is a rotation. So this is a long history. There are several names here. And I have variations also on this theme. But so this is, the group is, now in this case, the ideal coordinates are the following, the cylindrical one, so T, rho, Z, and phi. And let me write in inverted comma the commutation relations. I know that phi is not a good variable. A better expression is this one. So the non-commutativity is between time and the angle. And phi, the angle in cylindrical coordinates, or phi, actually is the same as the polar coordinates. Okay, I have to resist the temptation of write delta t, delta phi, because this is a question that is asked in exams in quantum mechanics. But I know how to deal with this non-commutation relation, because this is the non-commutation relation of Lz. And the thing is that this operator has a discrete spectrum. Now, it has a discrete spectrum, so time is discrete, and a change of basis is given by Fourier series. And so this is the delta. And if I, after a time measurement, I just collapse into a time. Again, an idea of numbers, the chronon, the unit of time, is very small. And if I want to have a localized space, now if I want to, the most accurate 10 to time is 10 to the 19. And this is a superposition of 10 to the 35 quanta of time. So this is the approximate Dirichlet function. And already when I go to 10 to 15, this is fairly localized. 10 to the 35 will be much more localized. And I want to finish by saying again, so I have a clock which scans the universe. Again, no, because the choice which I make is a choice of time, but I know that there are several self-adjoint extensions of this operator, the momentum on the circle. And therefore, any observer will have its own time, but different observers have different origins. And so there isn't a universal clock. There are observers which have discretized time. And okay, this I'll skip. We studied this non-commutativity with the Serbian group, Maria Dimitrijevic and Nikola Konjik and other people, and there are several papers which I have no time to discuss. Let me, I think a couple of minutes, yes, exactly 1 minute and 4 seconds, and the final remarks, but they have a postscript. And the main message I want to convey is that there is quantum space-time, and quantum space-time will require quantum observer. And this is true for quantum space and quantum phase space as well, and this is the challenge. I promised a postscriptum. The postscriptum in the 30 seconds which last are the rest of the acknowledgement of my thesis. And I decided to put it here because this is a way to remember old friends and to remember what for me is the most formative period of my life, which were the years in Syria. Some of the friends are not here anymore. So I was thanking Karl Rosenzweig, and I was thanking colleagues Gianni Sparano, and with whom I shared a discussion of physics and few Grand Cru. Grand Cru are the best wines from Bordeaux. I was there with Nair, Rajiv, Al Stern, and they are still around. And some people I lost, like Track, I have no idea what they do, Harald Gom. Some people we lost because Kamesh and Omer Kamachalan are not anymore with us. And okay, this is the rest. I thanking places where I was, including this was the Eastern Music Festival because I was dating a cellist at the time, and I was tongue-in-cheekly, part of the thesis was written when I was visiting her at this Eastern Music Festival. But as I said, for other reasons, I looked at this thesis and not long ago, a month ago or something like that. And I think it's fitting to remember what for me and for the people named here and the students that came before and after, what has been, I think for all of us, one of the most important periods of our life. And this has been the years that we spent with BAL as students. Okay, thank you very much. And this is those of you that were in Syracuse will recognize the modern version of this room. Okay, thank you.
Thank you, Fedele, for a very clear talk. We should open the floor to questions.
Hello, Fedele. Annisha here. So probably you have answered my first question, but you were very quick in that slide, so I want to verify that the concept of localization and the localization of a point with respect to different observers, which you just discussed, is it related with the concept of relative locality?
It is ideologically, this is the comment I did. We get to the same conclusion.
Yes.
Namely, that far away things can be not well localized. I claim that we are more rigorous because we do the theory of operator on Hilbert spaces. Localization is a measure, and we are in, so in this context, the intuition of Gianni, Jerzy, Laurent, and Lee is more based on the curvature of momentum space. Here we don't have momentum space. The two things are obviously connected, but at a deeper level, which I started to investigate in a paper called Double Quantization, trying to do some non-commutative geometry of quantum space-time. There are problems because time in quantum mechanics is not a good operator. It's a bad, it's not a good, it cannot be seen as an operator. So either one should go to quantum field theory, but even there things are complicated, or should understand the role of time in this in a better way.
Okay, and one more question. If I understood correctly, your translation generators are not commuting, am I right?
Yes.
So
You are right. Their commutation relation is exactly the same as the kappa Poincaré,
yes, yes.
the kappa Minkowski ones. So A0 commutes with everything because they cancel, and A0 AI equals I lambda AI.
Yes, so in context of this point, so a la Max Born's, can you say that the space-time is curved here? So we know that there is a duality between the curvature of space-time and non-commutativity between the translation generators. So what is your comment on that in this case?
That I would like to know, to understand it better. This is the key, this is the connection between the 2 points of view. Namely, if you have this, then your momentum space is curved. But we don't use this explicitly, this momentum space curvature, because we don't have momentum space, we don't have momentum here. And
so
now
these are not, you are not identifying these as your momentum.
I don't have momentum in this. I have kinematics. I don't consider momentum in this paper. So of course, this is the parameters when I do the group. This is the parameters of the momentum. So so I don't have a group. Those are the coordinate parameters of the momentum transformation, the e to the I a mu p mu. So and they don't commute. So since they don't commute, the momentum space is curved. And so this is the, I think was Jerzy Kowalski-Glisman, the first one that noticed this. I'm not 100% sure, but he was the first one to say this. So if I put momentum in this scheme, the momentum will be curved. And but I do everything without momentum. I'm kinematical basically here. So I'm describing this space-time and I'm describing the observers looking at this space-time. Now, when these observers will start moving and I will put a complete dynamics, then something will happen. I don't even have a Schrödingerish equation in this case.
Okay.
So I'm behind that.
Okay.
And with papers, now there is no time really to comment, but in papers with Flavio Mercati, we were trying to study the momentum space also with this point of view, but there are no complete understanding, let me say, of the connection.
Thank
so there
you.
is
Question from Bal.
Obvious understanding of the fact that there is a connection, but not of this connection. And now comes Bal. And I am again a student and fearing this question. Go ahead, Val.
Ciao, Fidele. There are a couple of things. First is, I don't know how one will do scattering theory in this model.
Which theory, I'm sorry?
In this kind of framework, for scattering, you should have localized wave packets which move in time, normally. Here, you can't do that localization because of this non-commutativity of this commutation relations between x and t that is involved here. So I don't quite know what is meant by scattering theory. How will I scatter things in this model? The second question is, unless the momenta translate positions, there is no experimental identification of what is meant by momentum. It is just a symbol in the model. Okay? If you identify positions as the coordinates, as a commutative algebra, you can think of it as a commutative algebra of space-time. But unless the operator which you call momentum translates these positions, there is no way to tell what it is. Because normally, a priori, there is no way, because the way one normally tells it is from exponential I p dot x, okay, that expression. But you can't write that if momenta don't translate positions. So I don't quite know what is meant by momentum here.
Okay, the second question, I agree. The first one.
One more thing. Sorry. You have a beautiful picture of 316. I don't know where you got it from, but it's very nice.
What you
the
send
table,
it to me.
with the table and the blackboards, whiteboards. Yeah.
You send it to me. You sent me two pictures. One with you, because when I was writing, I don't know if the volume is already available, but the volume celebrating you, my contribution is called 316. And I brought to you, and you had Indra take a picture of 316, and so probably Indra sent it to me.
Probably.
You are my connection. There is no one else in Syria. Well, I could have asked Carl, but unfortunately, I actually looked at it. I don't have any 316 picture of the 316 I know, the one in 1980. But I will have to do with the new one. The good thing is that 316 is still there, and is there also virtually, because it has been mentioned, the Anwesha talk that she gave in the seminar series of Room 316. Now, it means that there is a locus of the soul which has lasted more than nearly 50 years, because when I arrived in Syracuse in 1980, 316 as a meeting room, or rather than physical room, was already there. So it's a remarkable achievement. I think that the Plato Academia, or the place where the Royal Society was meeting, didn't last 50 years. They probably changed it, but so it's a remarkable achievement. Very quickly, because I'm cutting into your coffee time. Scattering. I thought of scattering. Scattering would be a fascinating thing, because it means that it's very difficult to localize an incoming state, but then the description is different if you are in the center of mass. So the observer is near the scattering, or you are translated from it. And of course, everything has to be done has to be transformed with these translations. I think there would be, so rather than having scattering, just the scattering process, pi going to gamma gamma, but the very process of scattering of ultra high energy would be different. So the idea of two particles going and then going away, it wouldn't work if you are at this very high energy. So again, I don't know, but because the in and out state, field theory, also this semi-classical, but in and out state, the definition of in and out state, it's very interesting, because you cannot localize them when you don't know where they're coming from, but you know when they arrive. It's like bad luck. You don't know where it's coming from. It's easily coming. When it hits you, then you can localize it. Okay.
So I think we are run out of time, but so let's thank Fedele again for a very clear talk.
Okay, you go for coffee. We all go for coffee.
it's on.
But also, more to the point is when time doesn't commute with space.
The time gets contest.
Then you have to do much more.
Yes.
Okay, so welcome to the post-coffee session. We are very happy to have Chandra Bhamidipati from IIT Bhubaneswar, and he's going to tell us about logarithmic corrections to black hole entropy and holography.
Okay, so let me start by thanking the organizers for giving me this opportunity. So I first met Bal long time in when I was a postdoc in Sao Paulo, in USP. I was with Paulo, and he said that Bal was visiting with TRG. So sessions used to start at 7 or 8 in the morning with black coffee, and by the time you know it was actually evening 5 p.m., 6 p.m., and there was no end to the discussions, and then it went on for a week, and after that all the concepts in the head were clear actually. So that's the memory I have, and so it's a great pleasure to speak here. Okay, so so the title is Logarithmic Corrections to Black Hole Entropy and Holography. This is some work in progress with my student Aritra Ghosh and Shudipta Mukherjee at IOP Bhubaneswar. So a couple of papers are published and one is in archive. So this is the outline of the talk. I will start with brief, just to recall some results on logarithmic corrections to entropy of black holes and what is called extended thermodynamics of black holes, which has new pressure and volume terms, and then come to computation of entropy corrections from energy and volume fluctuations. So this part is new, and discussing holography with these new pressure and volume terms. And towards the end, mention some novel logarithmic corrections to entropy of BTZ black holes in a holographic setting, which is a new setting, and we'll discuss about that as well. And I'll end with some open questions. Okay, so one of the tests of any theory of quantum gravity is a successful comparison between the macroscopic and microscopic predictions of black hole entropy. So the leading contribution to the black hole entropy is of course given by the Bekenstein-Hawking formula, area over 4G, and in these units, G is the Planck length squared, the Newton's constant. And this should agree with the logarithm of the microstate degeneracy. Okay, both can be computed independently, at least in some models, and the idea is that both should agree. That's a good test of your quantum gravity. Now, there is also another property that can be computed from the infrared physics, and that is the logarithmic corrections to black hole entropy. Because the microstate degeneracy can be computed. When you compute it, it also takes care of the UV part of the theory. but the logarithmic corrections you can compute in infrared physics. Particularly for large black holes, the dominant contribution to entropy comes from Bekenstein-Hawking term, but it can receive subleading corrections proportional to the logarithm of the horizon area. There have been several ways to compute these corrections in literature. For example, one loop contribution to black hole partition function, particularly for black holes in string theory, where you have extremal black holes, BPS black holes, you can compute these corrections. And also in loop quantum gravity. And one particular type of computation, which I will discuss further, which is the contribution coming from thermal fluctuations to entropy around equilibrium. Okay, I'll try to be brief here. Logarithmic corrections, particularly, for example, if you take one example of a BTZ black hole, logarithmic corrections have been computed both in the microscopic and macroscopic setting, long back by Karlip, TRG and collaborators, excuse me, Maldasena and collaborators, and Das, Majumdar and Bhaduri. So the corrections go like this. So if you take S0 to be your equilibrium entropy, then the logarithmic corrections goes as the variance in the energy. Okay, so energy, because there are thermal fluctuations, you have kept the system in contact with a thermostat, so there are fluctuations in energy, and those fluctuations contribute to the logarithmic corrections. And this was computed long back by Das, Majumdar and Bhaduri, and this turns out to be temperature square times C, where C is the specific heat of the system. So for the fluctuations to make sense, the specific heat has to be positive. That also is like one way to see the stability of the system. And the coefficient was extracted to be 3/2. Okay, this is the coefficient for log corrections. Now you can ask, what about the other type of fluctuations? So here we are talking about thermal fluctuations, okay, thermal fluctuations, but there can be other type of fluctuations. Particularly if you look at the first law, apart from the TDS term, there can be an angular momentum and its conjugate, charge and its conjugate. So they can also contribute to, they can also fluctuate and they can modify your log corrections. But apart from these, there are other important corrections, there are other important terms which are missing, notably the pressure and volume terms. Because they will be more fundamental if you have those terms, you can study their fluctuations as well, and they will be more fundamental than the other terms, work terms which you have here. So there have been several works in this. For example, if you can see here Brian's very nice paper, where there were questions about where is this term in the first law of black hole mechanics and what are the problems associated with it. How do we get these terms? Why there is no term like a volume? How do you define a volume for a black hole? Naively, it will be problematic to define volume for a black hole because the horizon, the horizon radius is time-like inside the horizon. If you start integrating from 0 to RH, then you don't know what you are, how you will define volume consistently. So the usual way to do black hole mechanics is to associate the mass of the black hole with the internal energy and have this kind of a first law. And if you have other terms, you add other terms here. So naively, if you associate, so this was discussed in one of the papers by Parikh as well. Naively, you can try to associate a volume to the black hole in this fashion, but then the internal energy will be a function of both entropy and volume, and since volume is already a function of horizon radius, entropy is also a function of horizon radius, so this description is a bit redundant and leads to some kind of an inconsistency. So the idea is that some progress can be made in spacetimes where you have a cosmological constant, and particularly if you can think of the cosmological constant as a dynamical variable. Now the idea of a dynamical cosmological constant is not new. In fact, there have been several works in literature where this idea has been floated. More recently, in this work which just appeared last week in Archive. So the idea is you associate a pressure to the cosmological constant in this fashion. Okay. Now there is strong evidence that cosmological constant is positive, but if lambda is positive, then immediately the pressure becomes negative, leading to a thermodynamic instability. Okay. So what we will do, at least for this talk, is restrict to lambda being negative so that the pressure turns out to be positive. And think of lambda as a thermodynamic parameter. Okay. Think of the cosmological constant as a thermodynamic parameter. There are, of course, other problems in de Sitter space. We will not go into it. So in this work, Castor, Ray and Trasher in 2009 showed that if you think of the cosmological constant as a thermodynamic variable, it also leads to the consistent SMAR formula for the ADS black holes. So in flat space, there is a SMAR formula, which is a simple scaling relation. If your mass depends on certain parameters, thermodynamic parameters, you can use a simple scaling relation to get a SMAR formula. In ADS black holes, if you try to repeat it, it turns out that unless you take variations of the cosmological constant as well, the SMAR formula does not come out to be correct. Okay. So this was shown in this paper. So here, this also requires, because of the way the first law appears once you write the SMAR formula, this also requires that the mass of the black hole has to be identified with enthalpy of the system, okay, not the internal energy. The usual ways to associate mass, black hole mass, to internal energy. So here it turns out you will have to associate it with enthalpy of the system. So this is what people do in chemistry, and that's why this line of work has been going on with the name as black hole chemistry. Okay. You can think of the PV term as mass energy of the black hole due to the negative energy density of the vacuum. Okay, so this is, you have cut out a volume from empty ADS to put a black hole in it, so that energy is minus PV, so that's what gives you the internal energy. Okay, so let's press on further. If you accept this, then the volume can be defined using the usual thermodynamic relations as del H by del P, and this has been called as the thermodynamic volume. So as we will see, thermodynamic volume is not necessarily same as the geometric volume which you would get, just naively integrating over the horizon. So the first law of black hole thermodynamics can now be written in this fashion, where apart from TDS, you have this VDP terms. So pressure is coming because of a variable cosmological constant, and the volume is nothing but its conjugate, okay, the way it should be in usual thermodynamics. So some of these relations already appeared earlier in slightly different guise for zero angular momentum. Okay, also Padmanabhan had it in his works. So I'll not go through the details here, but let me quickly mention that if you take a charged black hole in ADS with the usual relations, except with a new ingredient that you take pressure to be this related to cosmological constant, then this temperature relation, you eliminate the you rewrite cosmological constant in terms of pressure, and you can get a nice equation of state. And if you try to plot this equation of state, you get the usual van der Waals kind of a behavior. Okay, so you have this phase transitions and also the second order critical point. So a lot of work has been done. So this was shown by Kubiznak and Mann, and even Dolan initially had it in his works. So many of the things which you do in usual van der Waals system can be mapped to the black holes. Why this is important? Because if you are trying to understand the degrees of freedom associated with the black hole, then this is one limit where, due to an analogy with the van der Waals system, you can try to map and try to understand in each phase what the black hole degrees of freedom might be doing. Okay. So this part I will not go into it. So I'll just mention that if you take a simple charged black hole or a Schwarzschild black hole, you try to compute the thermodynamic volume. The thermodynamic volume comes out to be exactly same as the geometric volume which you compute. So this is good as well as bad. It's good because it's matching with your standard definition of geometric volume, but it's bad because you wanted to solve a problem That's why you introduce the dynamical cosmological constant, and you're still getting the same result. Okay? So fortunately, it turns out that this is just coincidental. If you take a rotating black hole and repeat the same computation, what you will note is that for a rotating black hole, the thermodynamic volume is not just the geometric volume, but there is also an additional contribution. So that's so if you put the angular momentum to 0, that is when the geometric and thermodynamic volume agree. Otherwise, the new thermodynamic volume, which is given here, does not agree directly with the geometric volume. It's different from it. And as a result, volume and entropy are not dependent on each other. Okay, they are independent parameters. That means you can have a consistent thermodynamics where you have entropy playing side by side with volume of the system as well. Now, if you ask me what is the physical meaning of this thermodynamic volume, I don't have an answer for that right now. Okay. Okay, so what is the, what was our aim? Our aim was to, so earlier, if you see, there were log corrections. Let me go back a couple of slides. Yeah, earlier there were these log corrections here to the entropy of black holes, which were computed in a setting where you had only thermal fluctuations. Okay. Now we have a setting where we have, apart from temperature, we also have pressure and volume terms. So it's very natural to ask, can you think of an ensemble where apart from thermal fluctuations, there are also fluctuations in volume? Suppose you keep the system in contact with not just a thermostat, but also a barostat, which controls the pressure. Then what you will have is, apart from fluctuations in energy, side by side, you will also have fluctuations in volume. Okay. It's very natural in thermodynamic setting to have such a situation. So if you do that, then you find that, so for the moment, if you keep the volume fixed, don't allow it to fluctuate, okay, just the thermal fluctuations, then the computation proceeds as before, and you get the log corrections proportional to T square CV. So earlier you had only T square C, but now you get T square CV, where CV is the specific heat at constant volume. Okay, previously there was no pressure and volume term, so it was a simple specific heat. Here it is specific heat at constant volume. So here the computation can proceed, and you find that the same corrections which were there before are reproduced. So nothing very new here. So I'll make one comment about this specific heat at constant volume. For a large class of black holes in ADS spacetime, particularly which are spherically symmetric, the specific heat at constant volume comes out to be 0. So if you calculate CV, it comes out to be 0. Okay. But if CV is 0, then that would mean there is a log times 0, and that is unwanted. Okay. So one can think of why it is coming out to be 0. If you take a rotating black hole, then the specific heat at constant volume is not 0. That's because entropy and volume are independent of each other. So that quantity is not 0. But if you take a highly spherically symmetric situation, that is when CV is coming out to be 0. Okay. Now, in a traditional thermodynamic setting, CV going to 0 is like very low temperature fluctuations. So one can think of a situation where CV is like proportional to Kb, the Boltzmann constant, and in some sense when you're saying CV equal to 0, you are thinking of Kb going to 0 limit. That's the kind of limit you are taking. So since it's a very small number, you can think of CV as a very small quantity, some epsilon, and in that, with this analogy, you can actually compute corrections, logarithmic corrections. Now, what I will do, I will describe a situation where you have, apart from fluctuations in, apart from thermal fluctuations, you also have fluctuations in volume. Okay, so now we are in an isothermal isobaric ensemble where you can control both the temperature and pressure. And if you do and repeat the computation and compute this coefficient D here, it turns out that the coefficient D now depends on all the variances. You have variance in energy, variance in volume, and there is also a cross term. Okay. This is not surprising. This was, if you compute, you will obviously get all these variances because you also have volume fluctuations. And there are other response functions which enter here, like isothermal compressibility is there, specific heat at constant pressure, etc. If you consider only thermal fluctuations, this is the result you get, but with combined fluctuations, this is what you have. Now, once you have temperature and volume fluctuations, you cannot just put one of the fluctuations to 0 and go back to the earlier canonical ensemble result. That you cannot do. Okay, so these are genuinely new corrections to the entropy of any thermodynamic system. Okay, so this is not necessarily for black holes. Any thermodynamic system you take, this is the kind of corrections you are going to get. For black holes, of course, you will have to identify the temperature with the Hawking temperature and pressure with the cosmological constant, and then you can check what the corrections are. So if you simplify, then D turns out to be T cube V Cv times kappa T. Okay, kappa T is the isothermal compressibility, Cv is specific heat at constant volume. So stability against thermodynamic fluctuations requires that this be greater than 0. So this is also required for log corrections to be meaningful in the Gaussian approximation. So one can calculate for rotating black holes, and the coefficient turns out to be 1, and this coefficient doesn't change from the earlier computations actually. In fact, one can repeat the computation for a large class of black holes, and you get varieties of coefficients in d dimensions. For example, Schwarzschild in d dimensions, you get this coefficient. But one should remember that when you are calculating this coefficient, there is a log of a small epsilon, which is like the Cv, which is present here for highly symmetric situations. Now that you have these corrections, it's a natural question to ask as to how do I check these corrections? How do I know that whether these corrections are correct or not? Otherwise, it will just be merely an academic exercise. You are just computing log corrections and you are getting various coefficients. So there has to be some way to check these corrections. So actually, when we tried, at that time there was not the holographic aspect of a dynamical cosmological constant was not clear. Okay. Fortunately, there were some developments. So this was the setting in the bulk which existed. So just to summarize this part, you have a black hole with mass m. You interpret m as the internal energy, sorry, enthalpy rather than internal energy. And this is the first law you get, and this is the SMAR formula. This last piece is the additional new piece. Now, you can ask a question, what is the holographic interpretation of a variable dynamical cosmological constant scenario? Okay. Now, the cosmological constant appears in this holographic relation where C is the central charge of the CFT, and okay, this should be capital L, and L is the cosmological constant and G is the Newton's constant. Alpha is a constant which depends on the details of a holographic theory depending on the number of dimensions, etc. So if you are in higher dimensions, this will turn out to be the number of colors if you are in n equal to 4 super Young-Mills. So if you try to vary the cosmological constant, it will automatically lead to variations in the central charge of the dual CFT, okay, assuming you are keeping the Newton's constant fixed. But changing the number of colors or the central charge of the CFT would mean there is some kind of an RG flow from one CFT to another CFT. Okay, so changing C scenario is not easy to handle. Now the second place where the variations in cosmological constant come, the effect of variable cosmological constant comes is the curvature radius of the manifold on which the field theory is formulated. So typically when you have this, when you have the ADS, there is a factor of R square by L square in the blackening factor. When you go to the boundary, you will have to multiply it with L square by R square to get the boundary metric. And there, if you see the volume of the CFT, that gets related to the cosmological constant. So radius of the dual field theory is also controlled by the cosmological constant. So if you change the cosmological constant in the bulk, you are also changing the volume of the dual CFT. Okay, that is the second, independently, that is the second place where the variation will come. Now the third place where the variation will come, when you vary the cosmological constant, the thermodynamic quantities in the bulk and the boundary differ by certain factors of L. Okay. So if you change the cosmological constant in the bulk, you will have to take care of all these three factors to ensure that, to see what exactly is happening in the boundary, dual field theory. So there have been some proposals. Most importantly, the proposal is to consider both the cosmological constant and also the Newton's constant to be thermodynamic parameters. Okay. So, variations in cosmological constant and is fine, but when you think of variations in the Newton's constant, so you have to think how would you address such a scenario. So fortunately, Bishwajit set up the stage in a few minutes back by taking G to 0 and H cross both to 0 by keeping the ratio to be constant. So in a similar setting, you could think of the cosmological constant and the Newton's constant to be thermodynamic parameters. There are of course other motivations as to why you would like to do that, because generally the cosmological constant comes from a higher dimensional theory because of from the vacuum expectation value of certain scalar fields, moduli fields, and if the moduli fields waves change, then the cosmological constant can also change essentially. Newton's constant can also be thought as coming from the dilaton coupling constant in higher dimensions. So there is some motivation how you would achieve these two, but the details have not totally been worked out. I mean, how would you exactly achieve a dynamical cosmological constant scenario or a dynamical Newton's constant? But for the moment, accepting that there is some way to get those corrections, from here what you can do is you can try to write this first law which you have here. So there is this first law here, okay, which has a V and a dP, etc. What you can try to do, you can try to rewrite this pressure term which you see here, which is coming from the cosmological constant, in terms of the variations of central charge and variations of the Newton's constant. So you start varying this, think of delta C and delta L and delta G, and substitute it back in the first law. Okay. So this was actually done by Mann and Kubiznak and Kong in last year in a very nice paper. And what they found is that they get a new mixed form of first law of black hole mechanics, where delta M is TdS plus Vc times dP, and there is a mu dc term, a new mu dc term. Okay. Mu is identified by taking derivative of this with the central charge, okay, delta M by delta C, and Vc is identified as delta M by delta P. This Vc is slightly different from the earlier thermodynamic volume which we had. So thermodynamically these relations are consistent. The new ingredient is a chemical potential, because you are in a situation where you are changing the central charge of the system, so obviously there will be a chemical potential dual to it, which will take care of the changes, right? So that actually appears in the first law. So what is our aim? Our aim was we already knew how to compute the log corrections in a setting where you have thermal fluctuations as well as there is pressure and volume terms. The idea is, in the presence of this additional term, what we wanted to do was to recompute those corrections, but now in a holographic setting, because now you have a variable central charge scenario. Okay. So before going to that computation, I will just summarize that computation only for the BTZ black hole. So let's briefly recall a few formulas for the BTZ black hole. So the BTZ black holes, the entropy, the black hole entropy, Bekenstein-Hawking entropy for the BTZ black holes can be computed in the dual CFT using the Cardy formula. Okay, so the Cardy formula is given here, where delta is the conformal dimension and C and C bar are the central charges of the CFT. Now, if you employ these relations where the conformal dimension is given in terms of outer and inner horizons, so if you consider a rotating black hole, you have outer and inner horizons, and the formula for the central charge which we saw before, G3 here is the three-dimensional Newton's constant. The Cardy formula can be rewritten in terms of the Bekenstein-Hawking entropy formula. This is well known. And states with large dimension in the conformal field theory are regarded as the microstates of the BTZ black hole. Okay. So the log corrections here have been computed and they have been matched, the bulk and boundary. Okay, so what did we do? What we did was we employed the same isothermal isobaric ensemble, okay, with the same variables. We held the central charge C fixed in equilibrium for the time being, and if you compute the corrections come out to be in this form. These are not very different from the earlier computation we did. The only difference is that the volume now has to be identified with Vc rather than the thermodynamic volume. Temperature is the Hawking temperature. Entropy is with the entropy of the black hole. And there is an additional scale which we need to fix. We took it as square of the Newton's constant. And this computation is general for any thermodynamic system, but for the BTZ black hole, we have to take these appropriate relations. So all the relations are actually known for the BTZ black hole. You know the temperature, pressure, etc. Only thing is you need to rewrite these quantities which are generally known in terms of the horizon radius in a slightly ugly looking fashion in terms of pressure and central charge, so they don't look familiar here. One very nice thing is that the specific heat at constant volume does not come out to be 0 even for a spherically symmetric black hole, which was a problem before because CV was coming out to be 0. Now in this mixed form of first law, here the CV does not come out to be 0. Okay, it's proportional to the entropy as it should be. So we computed the log corrections and this is what we get. Okay, so we have a factor of 3 in the front instead of 3 by 2, and there is an additional 2 log C piece which appears. Now the leading coefficient of -3, which is here, it matches with the earlier results of Carlip and also which was computed by Sen for a varieties of systems in a very nice paper. Many results were summarized here. But this differs by a factor of half with the computation of Majumdar and Kaul. We believe that's partly because there were only thermal fluctuations and there are no volume fluctuations. So we got an additional half from the volume fluctuations, and that gave a factor of 3 here. So these computations were done for neutral BTZ black holes, and at least there was a comment in Carlip's paper that if you consider neutral black holes, there will be an additional half factor coming from that. But if you just follow thermal fluctuations, there is no way to get that additional factor of half. Okay. Now we also get an additional 2 log C piece. C is the central charge, and this 2 log C, at least in a bulk calculation, has not appeared before to our knowledge. Carlip in his paper already had this result with a 2 log C. Okay, this result was already there in Carlip's paper, but now it comes out from a bulk calculation. There is also another way to obtain these corrections. What you do is you think of you try to think of a phenomenological way of writing the entropy in terms of the temperature of the left and right moving CFTs, and with some suitable normalization coefficients. Then you expand this entropy and try to find out the saddle points, and that itself also gives you the expression for entropy. And this also matches with the, so if you use this expression and compute, this will give you the same result actually, what you have here. So some similar expression was already proposed long back by Das, Majumdar and collaborators based on the modular invariance of the dual CFT, because there is a high temperature, low temperature connection because of the modular invariance of the dual CFT, and that motivates this kind of a form for the entropy. Computations for general black holes turns out to be very difficult, at least we have not been able to do yet. But in the high temperature limit, in d dimensions, you can compute the corrections to entropy, and this is how they look. Okay. In the CFT, we could not find a coefficient 2 by d minus 2, so we don't have anything to compare right now. But this coefficient is same as what Kaul and Majumdar computed, Bhaduri and Majumdar computed, but with an additional half as before. Okay, so they had 1 by 2 in the here, and we get something multiplied by 2. So how do you check whether this result is correct or not? So we have this CFT relation. We have this phenomenological relation for entropy motivated from modular invariance, and if you use this in d dimensions, that also gives rise to the same relation. Okay, so bulk and boundary, there is at least one way to compare that results. Okay, so this is pretty much the computation. So now what I will do is I will give a couple of speculations. So first thing is, Cardy's formula is actually valid in a regime where you keep the central charge of the CFT fixed, but you take operators of very large conformal dimension. So delta by C actually goes to infinity. That is the Cardy regime, asymptotic growth of states. Whereas the semi-classical black hole regime is where the central charge goes to infinity by keeping delta by C fixed. Okay. Now, how do you take central charge to infinity? So, when you are thinking of taking central charge to infinity, several works exist in literature. There is a long list of works actually as to how to reconcile these two regimes, and at least one moral how to reconcile these two regimes is to consider an n-fold symmetric product of certain seed CFTs such that each CFT has a fixed central charge. So, you take a CFT, let us say C equal to 24, and you take n copies of the CFT, then the total central charge is 24 times n. You can take n to be infinity, that is number of copies to be infinity, okay. But the central charge of the seed CFT remains fixed at 24. So, you are essentially using one CFT, but several copies of it. There is a long list of works whether such kind of symmetric product CFTs give you a proper description and whether proper black hole microstates. The bulk also has to satisfy stringent constraints, and this is not a complete, this story is at least not complete how to achieve that. Okay, there are several interesting works, but it's not complete, this story. But when you take C equal to 24, that is called the monster CFT, and for this particular case, the partition function can be computed at least in some limits. Okay. So, how do you compute the partition function? So, you consider a family of chiral CFTs with very large central charge, C equal to 24n, such that as n goes to infinity, C goes to infinity. For each of these CFTs, you can write the partition function in the usual fashion, where q is e power 2 pi I tau, that is the modular parameter. And if you want the partition function for the product CFT, this can be obtained from the DMVV product form, digraph and collaborators. So, this can be written in this fashion. Here, apart from q, you also get an additional p, where p is e power 2 pi I rho. So, rho is like a second modular parameter apart from tau, and rho takes care of the change in the number of CFTs basically. So, it's like a chemical, it's like, this is like a chemical potential actually, which takes care of the change in the number of CFTs. So, what you have here is a new dual modular symmetry, and rho also transforms under SL2Z. Just like tau transforms under SL2Z, rho also transforms. So, just like tau going to -1/2 relates high and low temperatures, rho going to -1/rho relates small and large values of n. So, what we tried to do, so this computation already existed, Verlinde, Lange, Maloney and Verlinde in a very nice paper, they actually already computed the asymptotic growth of states, the Cardy growth of states. So, what we all we did was to compute this additional factor, and if you rearrange and write the degeneracy of states, you get this familiar form, and from this the log corrections can be extracted, and these are same as the ones which we computed in the bulk. Okay, so, the bulk and the boundary both give the same result here. Of course, there are some things which one should remember, that these are chiral CFTs, and the story of chiral CFTs dual to black holes is not clear. Okay. So, we had to assume that although the computation was done for a chiral CFT, it could be done for a non-chiral CFT as well. So, this is a big if, so this is not complete yet. Okay. So, I'll end with some open questions. So, the idea is the computation, the computation of logarithmic corrections to entropy can be set up very nicely in a new situation where apart from thermal fluctuations, you also have fluctuations in the volume. But the computation should be repeated for rotating black holes and in particular rotating BTZ black hole. What is not clear is that what is the microscopic interpretation of having a situation where you have a dynamical cosmological constant or a variable Newton's constant. How do you interpret it from the microscopic side? That is not clear. Probably the possible way to, next thing to do would be to compute to actually do a Euclidean path integral computation in a dynamical cosmological constant scenario. So this partition function is there in Sain's paper, and one could try to do the computation in a grand canonical ensemble. So we are in an isothermal isobaric ensemble where we took the central charge essentially to be fixed. Okay. One should repeat the computation in a grand canonical ensemble to see further progress. Okay, so I'll stop my, I'll end my talk here with a photograph with Bal, which take a selfie I took last time I visited IMSC, and where Bal was working very seriously at night. So I would like to thank the organizers, and thank you. Congratulations.
So thank you, Chandra, for an interesting talk, and let's see if we have any questions.
Just a comment. From what I remember, the central charges, Beresford algebra, you have to take co-products, and the central charges, from what I remember, do not add. So, but here the addition formula was written. That doesn't seem correct to me.
You mean the Cardi formula, or no?
No. To get very large central charge,
yeah,
somebody took several copies.
Yeah.
That I don't know whether. What I know is that the co-product on the Beresford algebra, which is necessary to see how it operates on tensor product of two vector spaces, the central charges do not add. That I know. Okay. So I don't remember the formula, but it is not additive. Okay.
Okay.
So that formula doesn't seem right to me. I am not sure.
Okay. This I need to check. This part.
Hello, I have a comment also. Number one, about 2 decades back, Ramesh called myself and Sunita, BTZ black hole Chern-Simons theory partition function,
yes,
can be exactly calculated.
Yes.
And we have done that thing.
Yes.
And the result which you're quoting is there in that paper itself.
Yeah, I think you missed the first part of the talk. So
okay. So that is there in that paper.
Yeah.
And along up to the log C term.
Yes.
Because we had to have there's a formal expression for the partition function. Okay. But if you want to calculate to semi-classical expansion, we have to do some expansion. And up to the log C term, we have explicitly written down there.
Okay.
And after about maybe about 10 years, there is work of Maloney and Witten.
Yes.
We talked about 3D gravity and BTZ black hole. They also have the same formula. And I did send it to Professor Witten, and he agreed with that. And but the calculation which they did was slightly different, the method. And he wanted to find out how these two methods can be compared. Okay. It is not clear. That's what he mentioned.
Okay.
So this thing is explicitly, exactly calculable in terms of theta functions.
Okay. Okay.
Explicitly there. And up to log C term can be semi-classical expansions can be done.
Okay.
So that's what I wanted to say.
Okay, thanks. Yeah, I was not aware.
Yeah, Professor Dolan has a question. You can unmute yourself.
Can you hear me?
Yes, yes.
Yeah, I just have a question about considering Newton's constant as a thermodynamic variable.
Yeah.
Do you have any feeling as to what the conjugate variable would be to Newton's constant? Is that related to chemical potential, or is it something different?
No, so here the Newton's constant has been kept more like a bookkeeping device, the variation. The final variation was written in terms of the central charge and the pressure. So the volume you see here is a, so the volume you see here, sorry, this volume is not the same as the thermodynamic volume which you saw earlier. So the variations of the Newton's constant essentially have gone into redefining the volume and getting a new term. So in that sense, the dual has not been discussed. That's a very nice question actually. Yeah.
So if there are no further questions, let us thank Chandra again.
Thank you.
The next talk will be by Sasha Penzul, and he's going to tell us about exact results in non-commutative ADS2 CFT1 duality. No, we can see just your video, live video, but not yet, not your screen yet. Yeah, we can see your screen.
Okay, cool. Okay. Hi. It's nice to participate in one more BalFest anniversaries. I'm pretty sure that we will participate in many more. So, unfortunately, I could not come. So, because I'm in the middle of the semester. So, but I'm glad to give a talk anyway. So the talk will be essentially like not repetition, but I mean exactly on the same topic as the talk which I gave recently in Corfu. So several people, of course, will see that this is essentially the same talk. But I still decided to give this talk because I mean, like non-commutativity and BAL, they have very long history, and especially in my case, that was the main topic on which I collaborated with BAL until recently. I mean, so just recently, we somewhat started working in a different direction. And also there is a positive thing that if the internet connection drops, you can just go to YouTube and listen the Corfu talk. So in any case, so though the title is some exact results, so exact results will come only like at the end because they're more or less technical. So the main point of the talk will be kind of motivation, why to do this stuff. In addition to the standard motivation, because this is fun and all stuff. So this is more or less the plan of the talk. As I said, we'll just discuss more or less the geometry of the ADS space in the Lorentzian signature, Euclidean signature. What is the specifics of two-dimensional case? And then we'll pass to commutativity and, as I said, some exact results. So mostly this project was initiated with Alan Stern 2-3 years ago, something like that. But Fidelia participated at some stage, and of course, I mean, there were contributions from our students. So the ADS, DS, and spheres, of course, I mean, they're very intimately related. So here's some standard things about the isometries, right? So just looking already isometries of different spaces, you can see that okay, so there should be some relations already on the level of the representations and all that stuff. And so, but in two-dimensional case, this relation actually is much deeper, which has its consequences. So meaning that specifying d equals to 2, you see that the various groups, they actually are the same groups. So meaning the isometry, for example, of the Lorentzian ADS2 and Euclidean ADS2, they're the same, and actually de Sitter also the same. What is different, actually, of course, cosmological constant and some reshuffling of the signature of the embedding space. So the main difference between Euclidean ADS and Lorentzian ADS is actually in the topology, not in the isometry. So as usual, when you consider Lorentzian signature, then you will have some closed time-like curves. So meaning that you will have some hyperboloid, rotational hyperboloid, where rotation will be exactly as shown in the picture. And so that's why whenever you consider Lorentzian ADS, you actually don't consider that embedding per se, but you consider universal covering, right? You just decomplexify the time direction. And that's why actually you have all those patches when you cover already this decomplexified ADS2 in this particular case. So this Poincaré patch, and you have all this possibility of the physical consequences depending on your choice of the coordinates, actually. So we will see that in the Euclidean case, the situation is somewhat different, but still we care about Euclidean case because our primary interest actually to do kind of, if you wish, like non-perturbative check of ADS CFT conjecture. So, but of course, I mean, first I would like to give some standard arguments. Why do we care about non-connectivity in this particular setting? Because there are many reasons why to care, starting with just pure mathematical ones. I mean, so, but because, as I said, our goal is to check ADS CFT correspondence, our take on the non-connectivity exactly as some non-perturbative quasi-classical effects of quantum gravity. So there are very well-known arguments why quantum gravitational effects should lead to some non-classical space-time. And arguments given by Friedenhagen, Doppler, Roberts, they're quite universal, meaning that they essentially are model independent. And of course, I mean, this audience knows very well those arguments. And they show that independently of what the theory of quantum gravity will turn out to be, actually, it should be some kind of non-commutivity. At least there should be a regime where the space-time appears as a non-commutative one. Then there is a general belief, I mean, I would say it's maybe not that general, but I mean, you would like to believe, I would like to believe that the symmetries, they're quite rigid things. So I mean that they survive for quite large scales. So meaning that even if the quantum gravitational effects will kick in, we still would like to have some models which respect the symmetries before the quantum gravity actually started to play some role. So maybe in some the symmetries will be somewhat modified. I mean, so but still it would be nice to have some non-commutative models of space-time which respect the regional symmetries. So classical example of that would be, of course, a fuzzy sphere, which is the most studied probably model for the non-commutative space, and BAL has made very important contributions to this model. So essentially, you can think of ADS too as some non-compact analog of a sphere. So that of course tells us that the whole business will be mostly about the representations. Okay, so so this is the argument. I mean, so I will not repeat it. I mean, due to Doppler, Fehrenhagen, Roberts, that quantum gravitational effects should lead to some space-time uncertainty relations, and the non-commutative algebra is the realization of those relations. Okay, so the fuzzy Euclidean ADS2, as I said, I mean, is a natural generalization of a sphere, of a fuzzy sphere. So that's why, of course, I mean, it's also it's been introduced already some time ago. So the idea is, as I said, exactly to have some non-commutative generalization such that still respects that SO21 or SU11 isometry in some sense. So that isometry should be implemented on the non-commutative algebra. So that is nicely done if you know that this ADS, Euclidean ADS, or actually not necessarily Euclidean, Lorentzian ADS2, has a natural Poisson structure with Killian vectors given by the Hamiltonian fields essentially associated with that Poisson structure. Okay, so and then if you have this structure, of course, I mean, then you know how to go ahead and quantize at least formally. So to do actual calculations, of course, you would like to have some kind of local coordinates. By actual calculations, I mean that to put some field theory and extract some corrections and all that stuff. I mean, typically it would be nice actually to have some analog of local coordinates. So many people, including Nassim, so we did that for fuzzy sphere, for example. So here, for fuzzy sphere, in some sense, it's more complicated because it's a finite-dimensional matrix model. So here, it will turn out infinite-dimensional because it's a non-compact. So in some sense, it will be easier to do in this non-compact case. So, but in the commutative case, as I said, there are many different coordinates, and depending on the situation, one or another set of coordinates would be preferable. So the standard ones, this Pfefferman-Graham set of coordinates, which leads essentially to what you call typically to Poincare patch. Right? I mean, so here is the metric. So, but the Poisson structure, Poisson brackets, not very much trivial, so they're quadratic. So it's not immediately at least obvious how to quantize in terms of these coordinates naturally. There are so-called global coordinates, also very natural ones, which have very nice property of having the canonical Poisson structure. So meaning that the at least formal quantization in terms of these local coordinates, and because you remember, as we will see, this is some non-compact space. So formally, you just quantize in terms of these coordinates as a Moyle plane. So what is very important, so in some sense, you can take this as a hint of some of ADS CFT correspondence, that these Killing vectors in these coordinates or in these coordinates, so these coordinates are much nicer to see. I mean, so the conformal boundary here in this Hoffman-Graham coordinates corresponds to z going to +0. And then, at least naively, you can see that the Killing vectors on the boundary, they do generate the one-dimensional conformal transformations. Okay, just usual translations, dilatations, and superconformal transformations. So this is another, this is the main reason why these ZT coordinates are quite convenient, because I mean, in terms of x to y coordinates, the conformal boundary corresponds to x and y going to infinity, and typically you want to bring your boundary to some finite distance, so you can actually analyze it much better from the point of view of just, what are natural boundary conditions, though of course it's equivalent. So as I said, quantization, of course, as usual, it's about representations. So SO21 or SU11 is a non-compact case, so clearly there are no finite dimensional unitary representations, and there are 4 families of infinite dimensional unitary representations. Those families are well known since 60s, no, probably 70s. So you would think that each representation should correspond to some physical situation. And as we will see quickly, in some sense, this is the case. So only one, these representations will correspond to the case of our interest. So those representations are classified by Cartan, of course. I mean, so Cartan clearly is just essentially physically the radius of ADS, or the radius of your embedding. So here's the Cartan alpha. Here we keep just as a deformation parameter to keep track of non-commutative effects. So epsilon, some another parameter. N is discrete, so it's really the spectrum of some variables will be discrete. Of what variable we will see later on. So anyway, so those are 4 series, and the identification could be done like more or less like that. I mean, so just looking at the Cartan, we see that for the principal series, the radius will be negative. So which corresponds, I mean, I wrote Minkowski, Lorentzian ADS2. Then there is supplemental series. Series, they also have a negative cosmological constant. But as you can see, the radius, so K controls the radius, as I said, radius cannot go to infinity, so it cannot be made classical. So it will be always a quantum case. So we call it quantum Lorentzian ADS2, meaning that quantum which does not have a classical limit. And then those remaining 2 series, discrete series, they correspond to this last free parameter epsilon being fixed, correlated with k, which controls the radius, they exactly correspond to the geometry, to the classical geometry of the Euclidean ADS2. So here is, as I promised, a striking difference between Euclidean embedding and Lorentzian embedding. So the Lorentzian embedding, you remember, was also hyperboloid, which you had to decompactify to get rid of those CTC. So the Euclidean case is also a hyperboloid, but which obtained by rotation around a different axis, and it's made of two disconnected parts. So it also has like two boundaries as a strip in the Lorentzian case, but those boundaries are disconnected. So those two series, this discrete series, they exactly correspond whether you want to work quantize like this half or this half. So that actually could be made very concrete when you look at the representation, because I mean this coordinate plays the natural role of radius, radial coordinate, and you can see that the representation of embedding coordinates will actually tell you whether you considering the embedding of the of this upper half of the ADS2 within ADS2 or lower half of ADS2. Just looking at the sign of the corresponding embedding coordinate global, not global, the embedding one, the three-dimensional space. So, but what is important that the radial coordinate gets really quantized. Okay, so this is the M is discrete. So in terms of the radial coordinate, the boundary, as I said, is at infinity. So that corresponds to this quantum number to be very large, point to infinity, strictly speaking. And it could be sent to infinity because it's infinite dimensional representation. So the representation could be established explicitly given really the representation of all the embedding coordinates, and as a consequence you can read off from here the representation of x1 of the radial coordinate, just like from here. If you take the difference, then you see that it is a radial coordinate. Radial coordinate is given by multiplication in this page. So here is the, you remember that in the commutative case we had this, the global coordinates and z and t. So the relation between z and r away from the boundary, z equals 1 over r. Okay, so because for r the r equals 0, this is the center of the ADS. So r goes to infinity. This is boundary. So 1 over r brings the boundary to plus 0. So, but as I mentioned, to quantize, it's much more convenient to use those global coordinates x and y. So here's somewhat quick and formal consideration, but you can at least pretend doing that much more rigorously. So of course you can easily go back and forth between x, y, and r and t. Quantize in terms of x and y, the small star, and then you can formally just go back using the classical change of variables, go back to r and t, or if you wish, z and t, So it's very surprising, at least to me, that the classical change of variable in the model star, so take this usual model star, the classical change of variables will lead to exact quantization of this Poisson bracket, means without any quantum corrections. So like, we formally just put t hat, g hat, z square hat, and the star which will realize this non-commutative algebra will be the model star just written in terms of the new variables, once again, without any quantum corrections. Because strictly speaking, you might have, you could, after quantization, you can have some quantum corrections, or non-commutative corrections. So, as I said, so okay, so that would be our non-commutative ADS2. Now we, of course, we would like to do something with that model, and as I said, our interest was to check ADS-CFT in some sense beyond the classical gravity limit, because as I said, from the, for example, from the Fredenhagen and company argument, you can see that non-commutativity, if it's really the effect of quantum gravity, this is a non-perturbative effect. Okay, because I mean the argument goes with the creation of black holes, and as we know, the black holes cannot be described. The creation of the black hole cannot be described by some perturbation theory. So. So very quick review, like 1 page, 2 pages, what we would like to do without entering whether ADS-CFT actually some valid and sound thing or not. I mean, so let us think that it makes sense, and we want just to check whether it makes sense beyond some approximation, or it's just like a really artifact of very high symmetry. So anyway, so we consider the scalar mode, the excitation of ADS by a scalar. So this is the most general scalar field theory interacting on ADS, on two-dimensional ADS, equation of motion, conformal dimensions, essentially. And what you do with this, as usual, so we just will follow the standard prescription, which could be motivated, of course. I mean, so you calculate the classical solution for this theory, and calculate on shell action. Because of the presence of the conformal boundary, that will be non-trivial, meaning that it will reduce, in the classical case, to the evaluation of the action on the boundary. Hence, this correspondence between the theory, whatever it is, which lives on the boundary. So in the commutative case, the whole thing could be done nicely, again, due to the very high symmetry of the space-time background, meaning that you can really calculate, find free solutions exactly. For the interacting theory, you can find the first non-trivial corrections in terms of lambda, in this interaction constant. You can plug it back. So this is the solution, of course. I mean, so the K being bulk to boundary propagator, G being bulk to bulk propagator, and plugging back. That's actually the main object which you typically have in this. Okay, so this is boundary, and in the case of the interaction, you have also some bulk contribution, of course. I mean, and the prescription, ADS-CFT prescription, is that now your action will become the functional of the boundary conditions, essentially. So phi0 is the some field which lives on the boundary, which controls the behavior of the solution in the bulk. So essentially boundary condition. So you treat those as being sources for some actual observables on the boundary. So I mean that this is a partition function, generating function. If you believe in that, then you just do the usual thing, right? I mean, you vary with respect to your sources, and you obtain correlators. So if you do that in classical case, that would be your answer, clearly showing that the boundary theory for those observables, unspecified, it's a conformal one, right? So we would like to do this as much as possible in the non-commutative setting. So in terms of this, either operators or star products, as usual, the action is really just copy-paste of the commutative one, but you should be just carefully put in, if you will, like star products. I mean, of course, it's more than that, but I mean, for us, it would be enough. So where is the information that this is a really a fuzzy non-commutative ADS2? Of course, in the kinetic term. Exactly like in the case of a fuzzy sphere. So if you just talk about the algebra of the fuzzy sphere, it will be just the full matrix algebra of n by n dimensions. So how do we know that this is really a sphere? In the kinetic term or in non-commutative Killing vectors, right? I mean, so the fact that the kinetic term has this form exactly is the one which tells us that we're working on commutative ADS2. So this is the geometry, non-commutative term controls the geometry. So why do we want to believe that some kind of ADS-CFT still should work? Because the strong form of ADS-CFT is the following, that if you have some space which asymptotically looks like ADS, then the theory on the boundary, some theory on the boundary, will fully control the bulk theory, meaning that including even quantum gravitational effects. So how would, I mean, our space is fully non-commutative space, so how do we know like that it should work in any case? I mean, so what is this asymptotic of ADS, etc.? So the first hint comes from here. So as I said, I mean, so of course, I mean, now we can quantize easily isometry, because remember the isometry, the commutative one was given by the Poisson structure. So now non-commutative isometry, preserving the algebra and deformed one, SU11, will be just given by the commutators of the embedding coordinates, essentially. Or you can rewrite that in terms of T in Z coordinates and star products. You will have the exact formula, actually, for the non-commutative killings. This delta being some notation, this is essentially non-local deformation of T derivative, essentially like sine of TT. But the point is that when you send Z to 0, so you understand that Z, because it's a star product, so it's like symbols of some actual operators. So when you send that to 0, then you see that these non-commutative killing vectors close to the boundary still produces the usual commutative conformal transformations. So in this sense, you can say that the boundary, that asymptotically, non-commutative ADS too still looks more and more like the commutative ADS. The additional support to this fact comes from the following, that if you write this star product in terms of ZT, as I said, I mean, it's a small written in terms of ZT, and use the fields with the correct boundary conditions, I mean, so we know what are the boundary conditions, that the star product will actually go to the usual dot product when Z goes to 0. In some sense, it's very similar to the, not in some sense, it's exactly similar to the Moyle case, right? I mean, so we know that if you consider fields more and more regular, then the Moyle, by regular meaning that they don't change a lot at the quantum scale, then of course, I mean, Moyle product should become just usual product. That's how you recover the commutative algebra. So, but at the end of the day, and so like this is the argument why we should believe that we do have asymptotic ADS. So then, of course, I mean, let's start with the free case. So strangely enough, I mean, so when we started, we could treat even the free case only perturbatively in the non-commutative parameter, independently of all those things which I said, that let's preserve symmetry and all the stuff, and still we failed badly to produce the exact solution. And so that's why this talk, because I mean recently we managed actually to show that actually the free case, massless and massive, it does have very nice closed expressions for the solution for the scalar field and the fermionic field. So as I said, this part is rather technical, but in very non-intellectual way. I mean, so you really have to do a lot of calculations without involving a lot of some complicated math. So very helpful that the Laplacian could be written actually in this form. So that was in some sense what helped us to solve. I mean, it's a trivial transformation, but somehow we missed it. So if you do that, then doing kind of like separation of
Sasha,
variables. Yeah.
You have 5 minutes left.
Yes. Yeah. Thanks. So doing the transformation, the separation of variable inspired by the commutative case, you can actually reduce this operator equation to the ordinary differential equation, just for the radial coordinate. And the point is that that is just usual Lysander equation, which you can solve once again, because I mean now it depends only on one operator, so it's just usual commutative variable. And so after that we ran some non-trivial checks whether you can recover a commutative result, whether you can recover some our previous results, as I said. I mean, so we obtained only some perturbative in non-commutivity result. So those checks, I mean, just requires some special functions, some properties of special functions. So I will not elaborate on that. And so here's the master's case. So very quickly, so in some sense, you don't have to treat fermions, you don't have to find solutions for fermions independently, because we managed to show that the Dirac equation for fermions, which takes this form after some manipulations, has a solution if you know the solution for the, at least in the master's case, if you know the solution for the bosonic case, for the scalar field, then actually you can map it to the solution, to the fermionic solution. So you just take some two component spinor, and this matrix will map it to the solution of this equation. So those Greek letters, they're just combination of coordinates t and r. And just to conclude, so what will happen if you plug that into this prescription for the ATS CFT? As I said, boundary looks commutative, so you really only like bulk contributions will produce some corrections to the possible ATS CFT. So because for the free case we had exact solutions, so for the free case we could explicitly calculate the exact correlator, which we obtained exactly in the conformal form, and only prefactor got some corrections. For the interacting case, unfortunately, we still don't control completely, so we still have only some perturbative results, which support the conclusion that 3-point correlator still also has conformal form, only with the some prefactor modified. So to conclude, I just want to say that I think it's a nice topic. Once again, independently whether you believe in ADS CFT or not, because I mean it's a complete calculation which allows you to do some non-perturbative tests of some ideas. I mean, so that shows actually the relevance of non-permittivity for these kind of calculations. It might give some ideas, better ideas, what is the dual side of this correspondence. Okay, so though it looks it should be like the simplest one, because it's, I mean, you cannot go like down, it's ATS2, CFT1. Still there is a lot of discussion what is actually the CFT1, because it cannot be just usual quantum mechanics and stuff. So this non-connectivity could give a very nice test to those considerations. So, and here exactly like what answers we already have by now, that we have some partial answer to exact results, unfortunately without interaction. We tested that for different, for scalar field, for spinor field, and this is what we want to see. I mean, so mostly this last line. So, because I mean, JT gravity recently has become of some very important, it has become very important topic exactly in this relation. This ATS2, CFT1. So we trying to like revisit JT gravity also in this non-commutative setting, and to see whether it will be helpful in clarifying some points. Okay, so I think that's what I wanted to say. So once again, thank you for your attention, and parabéns, congratulations to BAL. Thank you very much.
Thank you, Sasha. Are there any questions?
Hi, Sasha. This is Kumar.
Oh, hi.
Hi. See, my question, at some point you said that you are assuming Brighton-Lohner-Friedman bound.
Uh-huh.
Now, we did the same analysis exactly for the same system, and we found that that particular bound picks up a correction from non-commutativity. Probably you know that calculation. So I'm wondering why you had to assume that it stays unchanged.
So here.
Yeah.
You're talking, I think it was your paper where you found some deformation, right, of CFT. Is that?
Right,
result
right.
you're talking
There
about?
was a deformation everywhere, both on the ADS side and the CFT side, and for the as a result on this bound, bright lunar feedback.
So in some sense, in this settings, this is just commutative one. So, but when you do the calculation in the non-commutative settings, we did not assume that. So it came out more or less exactly the same delta came out in the non-commutative calculation. So let me see. Here in these calculations, the same thing came out. You see this new.
Right, we got a different new. Our new picked up a correction.
Right. So I think I should look more carefully. I think probably some starting points or some settings were different. So that's why in your model you do have corrections, and in this model we don't. So I remember that I was looking at, but now I forgot actually the details. But the point is that here we don't assume it. It's just if you violate, then of course new becomes complex, and you just have completely different solutions, which will be having for us wrong boundary asymptotics and all this stuff. So here it just came as being result more or less the same way as in the classical case. But I have to look and try to pinpoint what exactly is different in our approaches.
Okay, thank you.
Mm-hmm.
Hi, Sasha. So
hey.
the question is,
Hi,
you're mentioning Green's functions. But the star product and so on involve infinite number of derivatives. And it is not clear that there is a propagation of an initial data which defines a globally hyperbolic problem. Then I do not see why Green's functions should exist at all in these problems.
Mm-hmm.
Am I wrong?
Right. No, you're not wrong. In some sense, that was my starting point, our starting point, in thinking. Because typically, as you know very well, so people doing some quite reckless stuff. They say, okay, so let's put just star products and delta function and try to proceed and all stuff. But then the question is, what is delta function? Because so if I just change the variables, the star product will change. What delta function you use there? Then people start putting some Gaussian regularization of delta function. So, but the point is that before going to star product, you can of course write, for example, equation, even interacting equation, just purely in terms of the operators. But then the problem should be just unique. So I just want to solve that operator equation. So when we say green function, that's exactly in the operator sense. Like I have equation like fg equals to some other operator. So I want to invert that. So in this sense, so exactly like in the case of the fuzzy sphere, right? In the case of the fuzzy sphere, you can write green function just expanding into spherical harmonics by truncating it. So, but the point is that because it will be given in terms of the operator, then it will be unique answer. You just, depending on what star product you use, you will have some expression. And because we're looking at the Euclidean case, of course, so I know that you don't like that, but in Euclidean case, it's not a hyperbolic problem, right? So it's an elliptic problem. So, but it will be still, of course, very highly non-trivial, non-local expression if you pass to symbols. So that would be my answer. But because we don't know the answer, I cannot say more and whether we will succeed or not.
It seems to me that, okay, I may be wrong. But it seems to me that there is no real propagation equation, because you will start getting pseudo differential operators. And then I have no
Right.
idea what how, there is no propagation equation, there is no Green's function. That I know.
Right.
So I don't know how to interpret your answer. Because there is.
Right.
So, okay.
Once again, you're right, but because the calculation, once again, this is a formal calculation, but because it's done in Euclidean case, we want to have a kind of bulk to boundary, but Euclidean one. So once again, so I cannot make more statements because, as I said, I'm far from controlling this question. So, but question is very important, and your question is exactly what started me thinking about that. Okay, thanks.
Okay, so are there any questions from Zoom? Okay, since there are no other questions, let us thank Sasha again.
Thank you.
And I will give the mic to TRG because he has some announcements.
Okay, so thanks a lot for the second day's program successfully carried out, and thanks Sachin and Denjo for chairing the sessions. Now, so tomorrow is a holiday, so you can go anywhere, and there are some transport numbers are available. You can book calling them and make your own arrangement easily. There are some places, and people have already are already doing. So that is first part. For those who are not going, who are going around here itself, who are breakfast, lunch, and dinner can be taken in the canteen. You just mentioned BalFest conference. That is enough, and that will be sufficient to tell. And those who are not taking, probably when you go outside, you will probably eat outside, and that will not. Which? That will be available. That ginger thing will be, whatever they give will be automatic. We are not concerned with that. Usually lunch and dinner and breakfast for the people here, and also Pallavaram guest house. So that is the second arrangement. And on Monday we will have a program as usual like this, whole day. And Tuesday's program, I just wanted to caution you, is not here. It will be held in IIT Madras. So there will be transport arrangements to go there, and IIT and exact location, etc. will be sent, and we'll make the arrangements for the Tuesday's program in IIT Madras in a hall which they are organizing. And Wednesday's program will be here, and Wednesday after probably around 3:30 we will have the felicitations, and FestScript book volume will be released around that time, and after that our program will be over. Okay, so this is the scheme of things to be followed, this thing. And there is anything else, Sujay, we have to tell? Okay, fine. Okay, thanks a lot again. Bye.